An upward view of bamboo trees. A bamboo forest in China. Credit, JF Zai/Flickr. Chapter outline. 4.1 Linear functions. 4.2 Modeling with linear functions. 4.3 Fitting linear models to data. Imagine placing a plant in the ground one day and finding that it has doubled its height just a few days later. Although it may seem incredible, this can happen with certain types of bamboo species. These members of the grass family are the fastest-growing plants in the world. One species of bamboo has been observed to grow nearly 15 inches every hour. One in a 24-hour period, this bamboo plant grows about 36 inches, or an incredible 3 feet. A constant rate of change, such as the growth cycle of this bamboo plant, is a linear function. Recall from functions and function notation that a function is a relation that assigns to every element in the domain exactly one element in the range. Linear functions are a specific type of function that can be used to model many real-world applications, such as plant growth over time. In this chapter, we will explore linear functions, their graphs, and how to relate them to data. Learning objectives. In this section, you will represent a linear function. Determine whether a linear function is increasing, decreasing, or constant. Interpret slope as a rate of change. Write and interpret an equation for a linear function. Graph linear functions. Determine whether lines are parallel or perpendicular. Write the equation of a line parallel or perpendicular to a given line. Front view of a subway train, the maglev train. Figure 1 Shanghai maglev train. Credit, Kangen/Flickr. Just as with the growth of a bamboo plant, there are many situations that involve constant change over time. Consider, for example, the first commercial maglev train in the world, the Shanghai maglev train, Figure 1. It carries passengers comfortably for a 30-kilometer trip from the airport to the subway station in only 8 minutes too. Suppose a maglev train travels a long distance and maintains a constant speed of 83 meters per second for a period of time once it is 250 meters from the station. How can we analyze the train's distance from the station as a function of time? In this section, we will investigate a kind of function that is useful for this purpose, and use it to investigate real-world situations, such as the train's distance from the station at a given point in time. Representing linear functions. The function describing the train's motion is a linear function, which is defined as a function with a constant rate of change. This is a polynomial of degree 1. There are several ways to represent a linear function, including word form, function notation, tabular form, and graphical form. We will describe the train's motion as a function using each method. Representing a linear function in word form. Let's begin by describing the linear function in words. For the train problem we just considered, the following word sentence may be used to describe the function relationship. The train's distance from the station is a function of the time during which the train moves at a constant speed plus its original distance from the station when it began moving at constant speed. The speed is the rate of change. Recall that a rate of change is a measure of how quickly the dependent variable changes with respect to the independent variable. The rate of change for this example is constant, which means that it is the same for each input value. As the time input increases by 1 second, the corresponding distance, output, increases by 83 meters. The train began moving at this constant speed at a distance of 250 meters from the station. Representing a linear function in function notation. Another approach to representing linear functions is by using function notation. One example of function notation is an equation written in the slope-intercept form of a line, where x is the input value, m is the rate of change, and b is the initial value of the dependent variable. Equation form function not a t, I, o, n letter 1d466 equals letter 1d45a letter 1d465 plus letter 1d44f letter 1d453. Letter 1d465 equals letter 1d45a letter 1d465 plus letter 1d44f. In the example of the train, we might use the notation where the total distance d is a function of the time t. The rate m is 83 meters per second. The initial value of the dependent variable b is the original distance from the station, 250 meters. We can write a generalized equation to represent the motion of the train. letter 1 d437, letter 1 d461, equals 83 letter 1 d461 plus 250, representing a linear function in tabular form. A third method of representing a linear function is through the use of a table. The relationship between the distance from the station and the time is represented in Figure 2. From the table, we can see that the distance changes by 83 meters for every 1 second increase in time. Table with the first row, labeled T, containing the seconds from 0, 1, 2, 3, and with the second row, labeled DT, containing the meters 250, 333, 416, and 499. Each value in the first row increases by 1 second, and each value in the second row increases by 83 meters. Figure 2, tabular representation of the function d, showing selected input and output values. Q&A. Can the input in the previous example be any real number? No, the input represents time, so while non-negative rational and irrational numbers are possible, negative real numbers are not possible for this example. The input consists of non-negative real numbers, representing a linear function in graphical form. Another way to represent linear functions is visually, using a graph. We can use the function relationship from above, letter 1 d437, letter 1 d461, equals 83 letter 1 d461 plus 250. To draw a graph, as represented in Figure 3, notice the graph is a line. When we plot a linear function, the graph is always a line. The rate of change, which is constant, determines the slant or slope of the line. The point at which the input value is 0 is the vertical intercept, or y-intercept, of the line. We can see from the graph that the y-intercept in the train example we just saw is 250, and represents the distance of the train from the station when it began moving at a constant speed. This is a graph with y-axis labeled distance, m, and x-axis labeled time, s. The x-axis spans from 0 to 5 and is marked in increments of 1. The y-axis spans from 0 to 500 and is marked in increments of 100. The graph shows an increasing function. As time increases, distance also increases. The line is graphed along the points 0, 250, and 1, 333. Figure 3, the graph of letter 1 d437, letter 1 d461, equals 83 letter 1 d461 plus 250. Graphs of linear functions are lines because the rate of change is constant. Notice that the graph of the train example is restricted, but this is not always the case. Consider the graph of the line letter 1 d453, letter 1 d465, equals 2 letter 1 d465 plus 1. Ask yourself what numbers can be input to the function. In other words, what is the domain of the function? The domain is comprised of all real numbers because any number may be doubled and then have 1 added to the product. Linear function. A linear function is a function whose graph is a line. Linear functions can be written in the slope-intercept form of a line. Letter 1 d453, letter 1 d465 equals letter 1 d45a letter 1 d465 plus letter 1 d44f, where b is the initial or starting value of the function when input, and m is the constant rate of change or slope of the function. The y-intercept is at 0b. Example 1. Using a linear function to find the pressure on a diver. The pressure P, in pounds per square inch, psi, on the diver in Figure 4 depends upon her depth below the water surface, d. In feet, this relationship may be modeled by the equation letter 1 d443, letter 1 d451 equals 0. 434d plus 14. 696. Restate this function in words. This figure shows a scuba diver. Figure 4, credit, Ilse Raibs and Jan Naud-Hutton. Solution. To restate the function in words, we need to describe each part of the equation. The pressure as a function of depth equals 434 thousandths times depth plus 14 and 696 thousandths. Analysis. The initial value, 14. 696 is the pressure in psi on the diver at a depth of 0 feet, which is the surface of the water. The rate of change, or slope, is 0. 434 psi per foot. This tells us that the pressure on the diver increases 0. 434 psi for each foot her depth increases, determining whether a linear function is increasing, decreasing, or constant. The linear functions we used in the two previous examples increased over time, but not every linear function does. A linear function may be increasing, decreasing, or constant. For an increasing function, as with the train example, the output values increase as the input values increase. The graph of an increasing function has a positive slope. A line with a positive slope slants upward from left to right, as in Figure 5a. For a decreasing function, the slope is negative. The output values decrease as the input values increase. A line with a negative slope slants downward from left to right, as in Figure 5b. If the function is constant, the output values are the same for all input values, so the slope is 0. A line with a slope of 0 is horizontal, as in Figure 5c. This figure shows three graphs labeled a b and c graph shows an increasing function, f, along the x-axis and the y-axis, which is labeled f of x. Graph B shows a decreasing function, f, along the x-axis and y-axis, which is labeled f of x. Graph C shows a constant function, f, along the x-axis and y-axis, which is labeled f of x. The constant function is horizontal. None of the graphs have any increments labeled on the x or y-axis. Figure 5. Increasing and decreasing functions. The slope determines if the function is an increasing linear function, a decreasing linear function, or a constant function. Letter 1D453. Letter 1D465 equals letter 1D45A letter 1D465 plus letter 1D44F is an increasing function if letter 1D45A 0. Letter 1D453. Letter 1D465 equals letter 1D45A letter 1D465 plus letter 1D44F is a decreasing function if letter 1D45A 0. Letter 1D453. Letter 1D465 equals letter 1D45A letter 1D465 plus letter 1D44F is a constant function if letter 1D45A equals 0. Example 2. Deciding whether a function is increasing, decreasing, or constant. Studies from the early 2010s indicated that teens sent about 60 texts a day, while more recent data indicates much higher messaging rates among all users, particularly considering the various apps with which people can communicate. 3. For each of the following scenarios, find the linear function that describes the relationship between the input value and the output value. Then, determine whether the graph of the function is increasing, decreasing, or constant. The total number of texts a teen sends is considered a function of time in days. The input is the number of days, and output is the total number of texts sent. BA person has a limit of 500 texts per month in their data plan. The input is the number of days, and output is the total number of texts remaining for the month. CA person has an unlimited number of texts in their data plan for a cost of $50 per month. The input is the number of days, and output is the total cost of texting each month. Solution. Analyze each function. A. The function can be represented as letter 1D453, letter 1D465, equals 60 letter 1D465, where x is the number of days. The slope, 60, is positive, so the function is increasing. This makes sense because the total number of texts increases with each day. B. The function can be represented as letter 1D453, letter 1D465 equals 500 minus 60 letter 1D465, where x is the number of days. In this case, the slope is negative, so the function is decreasing. This makes sense because the number of texts remaining decreases each day, and this function represents the number of texts remaining in the data plan after x. Days. C. The cost function can be represented as letter 1D453, letter 1D465 equals 50. Because the number of days does not affect the total cost. The slope is 0, so the function is constant, interpreting slope as a rate of change. In the examples we have seen so far, the slope was provided to us. However, we often need to calculate the slope given input and output values. Recall that given two values for the input, x1 and x2, and two corresponding values for the output, y1 and y2, which can be represented by a set of points, x1, y1, and x2, y2, we can calculate the slope m. Letter 1D45A equals change in output, rise change in input, run equals letter 1D65, letter 1D466, letter 1d65 letter 1d465 equals letter 1d466, 2 minus letter 1d466, 1 letter 1d465, 2 minus letter 1d465, 1. Note that in function notation, we can obtain two corresponding values for the output y1 and y2. For the function f, letter 1d466, 1 equals letter 1d453, letter 1d465, 1, and letter 1d466, 2 equals letter 1d453, letter 1d465, 2. So we could equivalently write letter 1d45a equals letter 1d453, letter 1d465, 2, letter 1d453, letter 1d465, 1, letter 1d465, 2, letter 1d465, 1. Figure 6 indicates how the slope of the line between the points x1, y1, and x2, y2 is calculated. Recall that the slope measures steepness, or slant. The greater the absolute value of the slope, the steeper the slant is. This graph shows how to calculate the slope of a line. The line is graphed on an xy coordinate plane. The x-axis is labeled from -1 to 6. The y-axis is labeled from -1 to 10. The line passes through several points, but two are marked specifically. The first is labeled x subscript 1, y subscript 1. It is located at the point 1, 5. The second point is labeled x subscript 2, y subscript 2. It is located at the point 2, 8. There is a small arrow that runs horizontally from point 2, 8 to point 1, 8. This arrow is labeled x subscript 2 minus x subscript 1. There is a blue arrow that runs vertically from point 1, 5 to point 1, 8, and is labeled y subscript 2 minus y subscript 1. Off to the side is the equation m equals delta y divided by delta x, which equals y subscript 2 minus y subscript 1 divided by x subscript 2 minus x subscript 1. Figure 6, the slope of a function is calculated by the change in y divided by the change in x. It does not matter which coordinate is used as the x2, y2, and which is the x1, y1, as long as each calculation is started with the elements from the same coordinate pair. Q and A. Are the units for slope always units for the output units for the input? Yes. Think of the units as the change of output value for each unit of change in input value. An example of slope could be miles per hour or dollars per day. Notice the units appear as a ratio of units for the output per units for the input. Calculate slope. The slope, or rate of change, of a function letter 1d45a can be calculated according to the following. Letter 1d45a equals change in output, rise change in input, run equals letter 1d65 letter 1d466, letter 1d65 letter 1d465 equals letter 1d466, 2 minus letter 1d466, 1 letter 1d465, 2 minus letter 1d465, 1. Where letter 1d465, 1 and letter 1d465, 2 are input values, y1 and letter 1d466, 2 are output values. How to, given 2 points from a linear function, calculate and interpret the slope. Determine the units for output and input values. Calculate the change of output values and change of input values. Interpret the slope as the change in output values per unit of the input value. Example 3. Finding the slope of a linear function. If letter 1d453, letter 1d465, is a linear function and 3 minus 2, and 81 are points on the line, find the slope. Is this function increasing or decreasing? Solution. The coordinate pairs are 3 minus 2 and 81. To find the rate of change, we divide the change in output by the change in input. Letter 1d45a equals change in output change in input equals 1 minus 2, 8 minus 3 equals 35. We could also write the slope as 6. The function is increasing because letter 1d45a 0. Analysis. As noted earlier, the order in which we write the points does not matter when we compute the slope of the line as long as the first output value, or y-coordinate, used corresponds with the first input value, or x-coordinate, used. Note that if we had reversed them, we would have obtained the same slope. Try it 1. If letter 1d453, letter 1d465, is a linear function and 23, and 4 are points on the line, find the slope. Is this function increasing or decreasing? Example 4. Finding the population change from a linear function. The population of a city increased from 23,400 to 27,800 between 2008 and 2012. Find the change of population per year if we assume the change was constant from 2008 to 2012. Solution. The rate of change relates the change in population to the change in time. The population increased by 27, 800 minus 23, 400 equals 4,400 people over the 4-year time interval. To find the rate of change, divide the change in the number of people by the number of years. 4,400 people 4 years equals 100 people. So the population increased by 1,100 people per year. Analysis. Because we are told that the population increased, we would expect the slope to be positive. This positive slope we calculated is therefore reasonable. Try it too. The population of a small town increased from 1,442 to 1,868 between 2009 and 2012. Find the change of population per year if we assume the change was constant from 2009 to 2012. Writing and interpreting an equation for a linear function. Recall from equations and inequalities that we wrote equations in both the slope-intercept form and the point-slope form. Now we can choose which method to use to write equations for linear functions based on the information we are given. That information may be provided in the form of a graph, a point and a slope, 2 points, and so on. Look at the graph of the function letter 1d453. In Figure 7, this graph shows a linear function graphed on an xy coordinate plane. The x-axis is labeled from -2 to 8, and the y-axis is labeled from -1 to 8. The function f is graph along the points 0, 7, and 4, 4. Figure 7. We are not given the slope of the line, but we can choose any 2 points on the line to find the slope. Let's choose 7 and 44. Now we can substitute the slope and the coordinates of one of the points into the point-slope form. Letter 1d466 minus letter 1d466, 1 letter 1d466 minus 4 equals letter 1d45a. Letter 1d465 minus letter 1d465, 1 minus 34 letter 1d465 minus 4. If we want to rewrite the equation in the slope-intercept form, we would find letter 1d466 minus 4 letter 1d466 minus 4 letter 1d466 equals minus 34. Letter 1d465 minus 4 minus 34 letter 1d465 plus 3 minus 34 letter 1d465 plus 7. If we want to find the slope-intercept form without first writing the point-slope form, we could have recognized that the line crosses the y-axis when the output value is 7. Therefore, letter 1d44f equals 7. We now have the initial value letter 1d44f and the slope letter 1d45a. So we can substitute letter 1d45a and letter 1d44f into the slope-intercept form of a line. This image shows the equation f of x equals m times x plus b. It shows that m is the value -3/4 and b is 7. It then shows the equation rewritten as f of x equals -3/4 times x plus 7. So the function is letter 1d453, letter 1d465, equals minus 34 letter 1d465 plus 7. And the linear equation would be letter 1d466 equals minus 34 letter 1d465 plus 7. How to? Given the graph of a linear function, write an equation to represent the function. Identify 2 points on the line. Use the 2 points to calculate the slope. Determine where the line crosses the y-axis to identify the y-intercept by visual inspection. Substitute the slope and y-intercept into the slope-intercept form of a line equation. Example 5. Writing an equation for a linear function. Write an equation for a linear function given a graph of letter 1d453. Shown in Figure 8. This figure shows an increasing function graphed on an xy coordinate plane. The x-axis is labeled from -10 to 10. The y-axis is labeled from -10 to 10. The function passes through the points 0, 2, and -2, -4. These points are not labeled on this graph. Figure 8. Solution. Identify 2 points on the line, such as 2 and -2, -4. Use the points to calculate the slope. Letter 1d45a equals letter 1d466, 2 minus letter 1d466, 1 letter 1 d465, 2 minus letter 1 d465, 1 minus 4 minus 2 minus 2, minus 0 minus 6 minus 23. Substitute the slope and the coordinates of one of the points into the point-slope form. Letter 1 d466 minus letter 1 d466, 1 letter 1 d466 minus 4 letter 1 d466, plus 4 equals letter 1 d45a, letter 1 d465 minus letter 1 d465, 1 3, letter 1 d465 minus 2 3, letter 1 d465 plus 2. We can use algebra to rewrite the equation in the slope-intercept form. Letter 1 d466 plus 4 letter 1 d466 plus 4 letter 1 d466 equals 3. Letter 1 d465 plus 2, 3 letter 1 d465 plus 63 letter 1 d465 plus 2. Analysis. This makes sense because we can see from figure 9 that the line crosses the y-axis at the point 0, 2, which is the y-intercept, so letter 1 d44f equals 2. This figure shows an increasing function graphed on an xy coordinate plane. The x-axis is labeled from -10 to 10. The y-axis is labeled from -10 to 10. The function passes through the points 0, 2, and -2, -4. These points are labeled on this graph. Figure 9. Example 6. Writing an equation for a linear cost function. Suppose Ben starts a company in which he incurs a fixed cost of $1,250 per month for the overhead, which includes his office rent. His production costs are $37, $50 per item. Write a linear function letter 1d436, where letter 1d436, letter 1d465, is the cost for letter 1d465. Items produced in a given month. Analysis. If Ben produces 100 items in a month, his monthly cost is found by substituting 100 for letter 1d465. Letter 1d436, 100 equals 1,250 plus 37. 100, 5,000. So his monthly cost would be $5,000. Example 7. Writing an equation for a linear function given 2 points. If letter 1d453 is a linear function with letter 1d453, 3 equals -2, and letter 1d453, 8 equals 1. Find an equation for the function in slope-intercept form. Solution. We can write the given points using coordinates. Letter 1 d453, 3 letter 1 d453, 8 equals -2 right arrow 3, -2, 1 right arrow 8, 1. We can then use the points to calculate the slope. Letter 1 d45a equals letter 1 d466, 2 minus letter 1 d466, 1 letter 1 d465, 2 minus letter 1 d465, 11 minus 2 8 minus 335. Substitute the slope and the coordinates of one of the points into the point-slope form. Letter 1 d466 minus letter 1 d466, 1 letter 1 d466 minus 2 equals letter 1 d45a. Letter 1 d465 minus letter 1 d465, 1, 35 letter 1 d465 minus 3. We can use algebra to rewrite the equation in the slope-intercept form. Letter 1 d466 plus 2 letter 1 d466 plus 2 letter 1 d466 equals 35. Letter 1 d465 minus 3, 35 letter 1 d465 minus 9,535 letter 1 d465 minus 195. Try it 3. If letter 1 d453, letter 1 d465, is a linear function, with letter 1 d453, 2 equals 11, and letter 1 d453, 4 equals -25, write an equation for the function in slope-intercept form. Modeling real-world problems with linear functions. In the real world, problems are not always explicitly stated in terms of a function or represented with a graph. Fortunately, we can analyze the problem by first representing it as a linear function and then interpreting the components of the function. As long as we know, or can figure out, the initial value and the rate of change of a linear function, we can solve many different kinds of real-world problems. How to? Given a linear function, letter 1 d453, and the initial value and rate of change, evaluate letter 1 d453, letter 1 d450. Determine the initial value and the rate of change, slope. Substitute the values into letter 1 d453. letter 1d465 equals letter 1d45a letter 1d465 plus letter 1d44f. Evaluate the function at letter 1d465 equals letter 1d450. Example 8. Using a linear function to determine the number of songs in a music collection. Marcus currently has 200 songs in his music collection. Every month he adds 15 new songs. Write a formula for the number of songs, letter 1d441, in his collection as a function of time, letter 1d461. The number of months. How many songs will he own at the end of 1 year? Solution. The initial value for this function is 200 because he currently owns 200 songs, so letter 1d441, 0, equals 200, which means that letter 1d44f equals 200. The number of songs increases by 15 songs per month, so the rate of change is 15 songs per month. Therefore, we know that letter 1d45a equals 15. We can substitute the initial value and the rate of change into the slope-intercept form of a line. This image shows the equation f of x equals m times x plus b. It shows that m is the value 15 and b is 200. It then shows the equation rewritten as n of t equals 15 times t plus 200. Figure 10. We can write the formula letter 1d441, letter 1d461, equals 15 letter 1d461 plus 200. With this formula, we can then predict how many songs Marcus will have at the end of 1 year, 12 months. In other words, we can evaluate the function at letter 1d461 equals 12, letter 1d441, 12 equals 15, 12 plus 200,180 plus 200,380. Marcus will have 380 songs in 12 months. Analysis. Notice that n is an increasing linear function. As the input, the number of months, increases, the output number of songs increases as well. Example 9. Using a linear function to calculate salary based on commission. Working as an insurance salesperson, Ilya earns a base salary plus a commission on each new policy. Therefore, Ilya's weekly income letter 1d43c depends on the number of new policies, letter 1d45b, he sells during the week. Last week he sold 3 new policies and earned $760 for the week. The week before, he sold 5 new policies and earned $920. Find an equation for letter 1d43c, letter 1d45b, and interpret the meaning of the components of the equation. Solution. The given information gives us 2 input-output pairs, 3,760 and 5,920. We start by finding the rate of change. Letter 1d45a equals 920 minus 7,600, 5 minus $3, 1,600, 2, policies, $80 per policy. Keeping track of units can help us interpret this quantity. Income increased by $160 when the number of policies increased by 2, so the rate of change is $80 per policy. Therefore, Ilya earns a commission of $80 for each policy sold during the week. We can then solve for the initial value. Letter 1d43c, letter 1d45b, 760,760,520 equals 80 letter 1d45b plus letter 1d44f 80. 3 plus letter 1d44f 80, 3 equals letter 1d44f, letter 1d44f, WHEN letter 1d45b equals 3. Letter 1d43c, 3, equals 760. The value of letter 1d44f is the starting value for the function and represents Ilya's income when letter 1d45b equals 0, or when no new policies are sold. We can interpret this as Ilya's base salary for the week, which does not depend upon the number of policies sold. We can now write the final equation. Letter 1d43c, letter 1d45b equals 80 letter 1d45b plus 520. Our final interpretation is that Ilya's base salary is $520 per week, and he earns an additional $80 commission for each policy sold. Example 10. Using tabular form to write an equation for a linear function. Table 1 relates the number of rats in a population to time in weeks. Use the table to write a linear equation. Number of weeks, W0246. Number of rats, P, W, 1,000, 1,080, 1,160, 1,240. Table 1. Solution. We can see from the table that the initial value for the number of rats is 1,000, so letter 1D44F equals 1,000. Rather than solving for letter 1D45A, we can tell from looking at the table that the population increases by 80 for every 2 weeks that pass. This means that the rate of change is 80 rats per 2 weeks, which can be simplified to 40 rats per week. Letter 1D443. Letter 1D464 equals 40 letter 1D464 plus 1,000. If we did not notice the rate of change from the table, we could still solve for the slope using any 2 points from the table. For example, using 21,080 and 61,240. Letter 1D45A equals 1,240 minus 10,806 minus 2,160,440. Q&A. Is the initial value always provided in a table of values like Table 1? No, sometimes the initial value is provided in a table of values, but sometimes it is not. If you see an input of 0, then the initial value would be the corresponding output. If the initial value is not provided because there is no value of input on the table equal to 0, find the slope. Substitute one coordinate pair and the slope into letter 1D453, letter 1D465, equals letter 1D45A letter 1D465 plus letter 1D44F, and solve for letter 1D44F. Try it 4. A new plant food was introduced to a young tree to test its effect on the height of the tree. Table 2 shows the height of the tree in feet, letter 1D465. Months since the measurements began. Write a linear function, letter 1D43b, letter 1D465, where letter 1D465 is the number of months since the start of the experiment, x0 2 4 8 12, hx12 5 13, 5 14, 5 16, 5 18, 5. Table 2. Graphing linear functions. Now that we've seen and interpreted graphs of linear functions, let's take a look at how to create the graphs. There are 3 basic methods of graphing linear functions. The first is by plotting points and then drawing a line through the points. The second is by using the y-intercept and slope. And the third method is by using transformations of the identity function letter 1D453, letter 1D465 equals letter 1D465. Graphing a function by plotting points. To find points of a function, we can choose input values, evaluate the function at these input values, and calculate output values. The input values and corresponding output values form coordinate pairs. We then plot the coordinate pairs on a grid. In general, we should evaluate the function at a minimum of 2 inputs in order to find at least 2 points on the graph. For example, given the function letter 1D453, letter 1D465 equals 2 letter 1D465, we might use the input values 1 and 2. Evaluating the function for an input value of 1 yields an output value of 2, which is represented by the point 12. Evaluating the function for an input value of 2 yields an output value of 4, which is represented by the point 24. Choosing 3 points is often advisable because if all 3 points do not fall on the same line, we know we made an error. How to? Given a linear function, graph by plotting points. Choose a minimum of 2 input values. Evaluate the function at each input value. Use the resulting output values to identify coordinate pairs. Plot the coordinate pairs on a grid. Draw a line through the points. Example 11. Graphing by plotting points. Graph letter 1D453, letter 1D465, equals minus 23 letter 1D465 plus 5. By plotting points, solution. Begin by choosing input values. This function includes a fraction with a denominator of 3, so let's choose multiples of 3 as input values. We will choose 0, 3, and 6, evaluate the function at each input value, and use the output value to identify coordinate pairs. Letter 1D465 equals 0, letter 1D465 equals 3, letter 1D465 equals 6, letter 1D453. 0 equals minus 23, 0 plus 5 equals 5, 0. 5 letter 1D453, 3 equals minus 23, 3, plus 5 equals 3, 3, 3 letter 1D453, 6 equals minus 23, 6 plus 5 equals 1, 6. 1. Plot the coordinate pairs and draw a line through the points. Figure 11 represents the graph of the function letter 1 d453, letter 1 d465, equals minus 23 letter 1 d465 plus 5. This graph shows a decreasing function graphed on an xy coordinate plane. The x-axis runs from -4 to 7, and the y-axis runs from -2 to 7. The y-axis is labeled f of x. The function passes through the points 0, 5, 3, 3, and 6, 1. Figure 11, the graph of the linear function letter 1 d453, letter 1 d465, equals minus 23 letter 1 d465 plus 5. Analysis. The graph of the function is a line as expected for a linear function. In addition, the graph has a downward slant, which indicates a negative slope. This is also expected from the negative, constant rate of change in the equation for the function. Try it 5. Graph letter 1 d453, letter 1 d465, equals minus 34 letter 1 d465 plus 6. By plotting points, graphing a function using y-intercept and slope. Another way to graph linear functions is by using specific characteristics of the function rather than plotting points. The first characteristic is its y-intercept, which is the point at which the input value is 0. To find the y-intercept, we can set. In the equation, the other characteristic of the linear function is its slope. Let's consider the following function. Letter 1 d453, letter 1 d465, equals 12 letter 1 d465 plus 1. The slope is 12. Because the slope is positive, we know the graph will slant upward from left to right. The y-intercept is the point on the graph when letter 1 d465 equals 0. The graph crosses the y-axis at 1. Now we know the slope and the y-intercept. We can begin graphing by plotting the point 1. We know that the slope is the change in the y-coordinate over the change in the x-coordinate. This is commonly referred to as rise over run, rice run. From our example, we have letter 1 d45a equals 12, which means that the rise is 1 and the run is 2. So starting from our y-intercept 1, we can rise 1 and then run 2, or run 2 and then rise 1. We repeat until we have a few points, and then we draw a line through the points as shown in figure 12. This graph shows how to calculate the rise over run for the slope on an x, y coordinate plane. The x-axis runs from -2 to 7. The y-axis runs from -2 to 5. The line extends right and upward from point 1, which is the y-intercept. A dotted line extends 2 units to the right from point 0, 1, and is labeled run equals 2. The same dotted line extends upwards 1 unit and is labeled rise equals 1. Figure 12, graphical interpretation of a linear function. In the equation letter 1 d453, letter 1 d465 equals letter 1 d45a letter 1 d465 plus letter 1 d44f. B is the y-intercept of the graph and indicates the point 0b, at which the graph crosses the y-axis. M is the slope of the line and indicates the vertical displacement, rise, and horizontal displacement, run, between each successive pair of points. Recall the formula for the slope. Letter 1 d45a equals change in output, rise change in input, run equals letter 1 d65 letter 1 d466, letter 1 d65 letter 1 d465 equals letter 1 d466, 2 minus letter 1 d466, 1 letter 1 d465, 2 minus letter 1 d465, 1. Q&A. Do all linear functions have y-intercepts? Yes, all linear functions cross the y-axis and therefore have y-intercepts. Note, a vertical line is parallel to the y-axis does not have a y-intercept, but it is not a function. How to? Given the equation for a linear function, graph the function using the y-intercept and slope. Evaluate the function at an input value of 0 to find the y-intercept. Identify the slope as the rate of change of the input value. Plot the point represented by the y-intercept. Use rice run to determine at least 2 more points on the line. Sketch the line that passes through the points. Example 12. Graphing by using the y-intercept and slope. Graph letter 1 d453, letter 1 d465, equals minus 23 letter 1 d465 plus 5, using the y-intercept and slope. Solution. Evaluate the function at. To find the y-intercept, the output value when is 5, so the graph will cross the y-axis at 5. According to the equation for the function, the slope of the line is minus 23. This tells us that for each vertical decrease in the rise of 2 units, the run increases by 3 units in the horizontal direction. We can now graph the function by first plotting the y-intercept on the graph in Figure 13. From the initial value, 5, we move down 2 units, and to the right 3 units. We can extend the line to the left and right by repeating, and then drawing a line through the points. This graph shows a decreasing function graphed on an xy coordinate plane. The x-axis runs from -3 to 7, and the y-axis runs from -1 to 7. The function passes through the points 5, 33, and 61. Arrows extend downward 2 units, and to the right 3 units from each point to the next point. Figure 13 graph of letter 1D453, letter 1D465, equals -2/3 letter 1D465 plus 5, and shows how to calculate the rise over run for the slope. Analysis. The graph slants downward from left to right, which means it has a negative slope as expected. Try it 6. Find a point on the graph we drew in example 12 that has a negative x value. Graphing a function using transformations. Another option for graphing is to use a transformation of the identity function letter 1D453. Letter 1D465 equals letter 1D465. A function may be transformed by a shift up, down, left, or right. A function may also be transformed using a reflection, stretch, or compression. Vertical stretch or compression. In the equation, letter 1D453. Letter 1D465 equals letter 1D45A letter 1D465. The letter 1D45A is acting as the vertical stretch or compression of the identity function. When letter 1D45A is negative, there is also a vertical reflection of the graph. Notice in Figure 14 that multiplying the equation of letter 1D453, letter 1D465 equals letter 1D465, by letter 1D45A, stretches the graph of letter 1D453 by a factor of letter 1D45A, units if letter 1D45A 1, and compresses the graph of letter 1D453 by a factor of letter 1D45A, units if 0, letter 1D45A 1. This means the larger the absolute value of letter 1D45A, the steeper the slope. This graph shows 7 versions of the function f of x equals x on an x, y coordinate plane. The x-axis runs from -8 to 8. The y-axis runs from -8 to 8. 7 multicolored lines run through the point 0, 0. Starting with the lines in the top right quadrant and moving clockwise, the first line is f of x equals 3 times x and has a slope of 3. The next line is f of x equals 2 times x, which has a slope of 2. The next line is f of x equals x, which has a slope of 1. The next line is f of x equals x divided by 2, which has a slope of 5. The last line in this quadrant is f of x equals x divided by 3, which has a slope of 1/3 x. In the bottom right quadrant moving clockwise, the first line is f of x equals -x divided by 2, which has a slope of -1/2. The middle line is f of x equals -x, which has a slope of -1, and the last line is f of x equals -2 times x, which has a slope of -2. Figure 14 vertical stretches and compressions and reflections on the function letter 1D453. Letter 1D465 equals letter 1D465. Vertical shift. In letter 1D453, letter 1D465 equals letter 1D45A letter 1D465 plus letter 1D44F. The letter 1D44F acts as the vertical shift, moving the graph up and down without affecting the slope of the line. Notice in Figure 15 that adding a value of letter 1D44F to the equation of letter 1D453, letter 1D465 equals letter 1D465, shifts the graph of letter 1D453, a total of letter 1D44F, units up if letter 1D44F is positive and letter 1D44F, units down if letter 1D44F is negative. This graph shows 6 versions of the function f of x equals x on an x, y coordinate plane. The x-axis runs from -8 to 8, and the y-axis runs -8 to 8. There are 5 lines parallel to each other. The first line extends from the bottom left quadrant to the upper right quadrant on the coordinate plane. This line shows f of x equals x plus 4, which has a slope of 1 and a y-intercept at 4. The next line also extends from the bottom left quadrant to the upper right quadrant and shows f of x equals x plus 2, which has a slope of 1 and a y-intercept at 2. The next and middle line extends from the lower left quadrant through the center of the graph at point 0, 0 to the upper right quadrant and shows f of x equals x. The next line extends from the lower left quadrant through the lower right quadrant to the upper right quadrant. This line shows f of x equals x minus 2, which has a slope of 1 and a y-intercept at minus 2. The last line extends from the lower left quadrant through the lower right quadrant to the upper right quadrant. This line shows f of x equals x minus 4, which has a slope of 1 and a y-intercept at minus 4. Figure 15, this graph illustrates vertical shifts of the function letter 1 d453, letter 1 d465, equals letter 1 d465. Using vertical stretches or compressions along with vertical shifts is another way to look at identifying different types of linear functions. Although this may not be the easiest way to graph this type of function, it is still important to practice each method. How to? Given the equation of a linear function, use transformations to graph the linear function in the form letter 1 d453, letter 1 d465, equals letter 1 d45a letter 1 d465 plus letter 1 d44f. Graph letter 1 d453, letter 1 d465 equals letter 1 d465. Vertically stretch or compress the graph by a factor letter 1 d45a. Shift the graph up or down letter 1 d44f. Units. Example 13. Graphing by using transformations. Graph letter 1 d453, letter 1 d465, equals 12 letter 1 d465 minus 3. Using transformations. Solution. The equation for the function shows that, so the identity function is vertically compressed by 12. The equation for the function also shows that letter 1 d44f equals minus 3. So the identity function is vertically shifted down 3 units. First, graph the identity function and show the vertical compression as in figure 16. This graph shows two functions on an x, y coordinate plane. One shows an increasing function of y equals x divided by 2 that runs through the points 0, 0, and 2, 1. The second shows an increasing function of y equals x and runs through the points 0, 0, and 1, 1. Figure 16. The function letter 1 d466 equals letter 1 d465, compressed by a factor of 12, then show the vertical shift as in figure 17. This graph shows two functions on an x, y coordinate plane. The first is an increasing function of y equals x divided by 2 and runs through the points 0, 0, and 2, 1. The second shows an increasing function of y equals x divided by 2 minus 3 and passes through the points 0, 3, and 2, minus 2. An arrow pointing downward from the first function to the second function reveals the vertical shift. Figure 17, the function letter 1 d466 equals 12 letter 1 d465. Shifted down 3 units, try it 7. Graph letter 1 d453, letter 1 d465, equals 4 plus 2 letter 1 d465. Using transformations. Q&A. In example 15, could we have sketched the graph by reversing the order of the transformations? No. The order of the transformations follows the order of operations. When the function is evaluated at a given input, the corresponding output is calculated by following the order of operations. This is why we performed the compression first. For example, following the order. Let the input be 2. Letter 1 d453, 2 equals 12, 2 minus 30, 1 minus 3 minus 2. Writing the equation for a function from the graph of a line. Earlier, we wrote the equation for a linear function from a graph. Now we can extend what we know about graphing linear functions to analyze graphs a little more closely. Begin by taking a look at figure 18. We can see right away that the graph crosses the y-axis at the point 4. So this is the y-intercept. This graph shows the function f of x equals 2 times x plus 4 on an x, y coordinate plane. The x-axis runs from negative 10 to 10. The y-axis runs from negative 10 to 10. This function passes through the points minus 2, 0, and 0, 4. Figure 18. Then we can calculate the slope by finding the rise and run. We can choose any 2 points, but let's look at the point 20. To get from this point to the y-intercept, we must move up 4 units rise, and to the right 2 units run. So the slope must be letter 1d45a equals rice run equals 42 equals 2. Substituting the slope and y-intercept into the slope-intercept form of a line gives letter 1d466 equals 2 letter 1d465 plus 4. How to? Given a graph of linear function, find the equation to describe the function. Identify the y-intercept of an equation. Choose 2 points to determine the slope. Substitute the y-intercept and slope into the slope-intercept form of a line. Example 14. Matching linear functions to their graphs. Match each equation of the linear functions with one of the lines in Figure 19. A letter 1d453, letter 1d465 equals 2 letter 1d465 plus 3. B letter 1d454, letter 1d465 equals 2 letter 1d465 minus 3. C letter 210e, letter 1d465 equals minus 2 letter 1d465 plus 3. D letter 1d457, letter 1d465 equals 12 letter 1d465 plus 3. Graph of 4 functions where the orange line has a y-intercept at 3 and slope of 2. The baby blue line has a y-intercept at 3 and slope of 1, 2. The blue line has a y-intercept at 3 and slope of minus 2. And the green line has a y-intercept at and slope of 2. Figure 19. Finding the x-intercept of a line. So far, we have been finding the y-intercepts of a function, the point at which the graph of the function crosses the y-axis. Recall that a function may also have an x-intercept, which is the x-coordinate of the point where the graph of the function crosses the x-axis. In other words, it is the input value when the output value is 0. To find the x-intercept, set a function letter 1d453, letter 1d465, equal to 0 and solve for the value of letter 1d465. For example, consider the function shown. Letter 1d453, letter 1d465, equals 3 letter 1d465 minus 6. Set the function equal to 0 and solve for letter 1d465. 0, 62, letter 1d465 equals 3 letter 1d465 minus 63, letter 1d465 letter 1d465 2. The graph of the function crosses the x-axis at the point 20. Q&A. Do all linear functions have x-intercepts? No. However, linear functions of the form letter 1d466 equals letter 1d450, where letter 1d450 is a non-zero real number, are the only examples of linear functions with no x-intercept. For example, letter 1d466 equals 5 is a horizontal line 5 units above the x-axis. This function has no x-intercepts, as shown in Figure 21. Graph of the function y equals 5, a completely horizontal line that goes through the point 5. Graphed on an xy plane with the x-axis ranging from minus 3 to 3 and the y-plane ranging from minus 1 to 8. Figure 21. X-intercept. The x-intercept of the function is value of letter 1d465. When letter 1d453, letter 1d465 equals 0. It can be solved by the equation. Example 15. Finding an x-intercept. Find the x-intercept of letter 1d453, letter 1d465, equals 12 letter 1d465 minus 3. Solution. Set the function equal to 0 to solve for letter 1d465. 0, 36, letter 1d465 equals 12 letter 1d465 minus 312 letter 1d465 letter 1d465 6. The graph crosses the x-axis at the point 60. Analysis. A graph of the function is shown in Figure 22. We can see that the x-intercept is 60. As we expected, graph of the linear function with the points 60 and labeled with a slope of a half. Figure 22. Try at 8. Find the x-intercept of letter 1d453, letter 1d465, equals 14 letter 1d465 minus 4. Describing horizontal and vertical lines. There are 2 special cases of lines on a graph, horizontal and vertical lines. A horizontal line indicates a constant output, or y value. In Figure 23, we see that the output has a value of 2 for every input value. The change in outputs between any 2 points, therefore, is 0. In the slope formula, the numerator is 0, so the slope is 0. If we use, in the equation letter 1d453, letter 1d465 equals letter 1d45a letter 1d465 plus letter 1d44f. The equation simplifies to letter 1d453. Letter 1d465 equals letter 1d44f. In other words, the value of the function is a constant. This graph represents the function letter 1d453, letter 1d465 equals 2. This graph shows the line y equals 2 on an xy coordinate plane. The x-axis runs from -5 to 5, and the y-axis runs from 5 to 5. A horizontal line crosses through the point 0, 2. Underneath the graph is a table with 2 rows and 6 columns. The top row is labeled x and has the values -4, -2, 0, 2, and 4. The bottom row is labeled y and has the values 2, 2, 2, 2, and 2. Figure 23, a horizontal line representing the function letter 1d453, letter 1d465, equals 2. A vertical line indicates a constant input, or x value. We can see that the input value for every point on the line is 2, but the output value varies. Because this input value is mapped to more than one output value, a vertical line does not represent a function. Notice that between any 2 points, the change in the input values is 0. In the slope formula, the denominator will be 0, so the slope of a vertical line is undefined. This is an image showing when a slope is undefined. M equals change of output divided by the change of input. The change of output is labeled as non-zero real number, and the change of input is labeled 0. Figure 24 example of how a line has a vertical slope. 0 in the denominator of the slope. A vertical line, such as the one in figure 25, has an x-intercept, but no y-intercept unless it's the line letter 1d465 equals 0. This graph represents the line letter 1d465 equals 2. This graph shows a vertical line passing through the point 2, 0 on an x, y coordinate plane. The x-axis runs from -5 to 5, and the y-axis runs from -5 to 5. Underneath the graph is a table with 2 rows and 6 columns. The top row is labeled x and has the values 2, 2, 2, 2, and 2. The bottom row is labeled y and has the values -4, -2, 0, 2, and 4. Figure 25, the vertical line, letter 1d465 equals 2, which does not represent a function. Horizontal and vertical lines. Lines can be horizontal or vertical. A horizontal line is a line defined by an equation in the form letter 1d453, letter 1d465, equals letter 1d44f. A vertical line is a line defined by an equation in the form letter 1d465 equals letter 1d44e. Example 16. Writing the equation of a horizontal line. Write the equation of the line graphed in figure 26. This graph shows the function y -4 on an x, y coordinate plane. The x-axis runs from -10 to 10. The y-axis runs from -10 to 10. The horizontal line passes through the point 0, -4. Figure 26. Example 17. Writing the equation of a vertical line. Write the equation of the line graphed in figure 27. Graph of x equals 7. Figure 27. Solution. The constant x value is 7, so the equation is letter 1d465 equals 7, determining whether lines are parallel or perpendicular. The 2 lines in figure 28 are parallel lines. They will never intersect. They have exactly the same steepness, which means their slopes are identical. The only difference between the 2 lines is the y-intercept. If we shifted one line vertically toward the other, they would become coincident. This graph shows 2 lines on an x, y coordinate plane. The x-axis runs from -4 to 6. The y-axis runs from -3 to 8. The first line has the equation y equals -3 times x divided by 2 plus 1. The second line has the equation y equals -3 times x divided by 2 plus 7. The lines do not cross. Figure 28 parallel lines. We can determine from their equations whether 2 lines are parallel by comparing their slopes. If the slopes are the same and the y-intercepts are different, the lines are parallel. If the slopes are different, the lines are not parallel. Letter 1d453, letter 1d465, equals -2 letter 1d465 plus 6 letter 1d453, letter 1d465, equals -2 letter 1d465 minus 4p, A R a L L E L letter 1D453, letter 1D465, equals 3 letter 1D465 plus 2 letter 1D453, letter 1D465, equals 2 letter 1D465 plus 2 not parallel. Unlike parallel lines, perpendicular lines do intersect. Their intersection forms a right or 90-degree angle. The two lines in figure 29 are perpendicular. This graph shows two functions perpendicular to each other on an x, y coordinate plane. The first function increases and passes through the points 1, 0, and 0, minus 5. The second function decreases and passes through the points 1, 0, and minus 4, 1. The lines intersect to form a 90-degree right angle at the point 1, 0. Figure 29 perpendicular lines. Perpendicular lines do not have the same slope. The slopes of perpendicular lines are different from one another in a specific way. The slope of one line is the negative reciprocal of the slope of the other line. The product of a number and its reciprocal is 1. So, if letter 1D45A1 and M2 are negative reciprocals of one another, they can be multiplied together to yield 1. Letter 1D45A1 letter 1D45A2 equals minus 1. To find the reciprocal of a number, divide 1 by the number. So the reciprocal of 8 is 18, and the reciprocal of 18 is 8. To find the negative reciprocal, first find the reciprocal and then change the sign. As with parallel lines, we can determine whether two lines are perpendicular by comparing their slopes, assuming that the lines are neither horizontal nor vertical. The slope of each line below is the negative reciprocal of the other, so the lines are perpendicular. Letter 1D453, letter 1D465, letter 1D453, letter 1D465, equals 14 letter 1D465 plus 2 minus 4 letter 1D465 plus 3 negative reciprocal of 14 is minus 4 negative reciprocal of minus 4 is 14. The product of the slopes is 1. Minus 4, 14 equals minus 1. Parallel and perpendicular lines. Two lines are parallel lines if they do not intersect. The slopes of the lines are the same. Letter 1D453. Letter 1D465 equals letter 1D45A, 1 letter 1D465 plus letter 1D44F, 1, a ND letter 1D454. Letter 1D465 equals letter 1D45A2X plus B2 are parallel if and only if letter 1D45A1 equals letter 1D45A2. If and only if letter 1D44F1 equals letter 1D44F2, and letter 1D45A1 equals letter 1D45A2. We say the lines coincide. Coincident lines are the same line. Two lines are perpendicular lines if they intersect to form a right angle. Letter 1D453. Letter 1D465 equals letter 1D45A, 1 letter 1D465 plus letter 1D44F, 1, a ND letter 1D454. Letter 1D465 equals letter 1D45A2X plus B2 are perpendicular if and only if. Letter 1D45A, 1 letter 1D45A2 equals minus 1. SO letter 1D45A, 2 equals minus 1 letter 1D45A1. Example 18. Identifying parallel and perpendicular lines. Given the functions below, identify the functions whose graphs are a pair of parallel lines and a pair of perpendicular lines. Letter 1D453, letter 1D465, letter 1D454. Letter 1D465 equals 2 letter 1D465 plus 312 letter 1D465 minus 4 letter 210e, letter 1D465, letter 1D457, letter 1D465 equals minus 2 letter 1D465 plus 22 letter 1D465 minus 6. Solution. Parallel lines have the same slope. Because the functions letter 1D453, letter 1D465 equals 2 letter 1D465 plus 3, and letter 1D457, letter 1D465 equals 2 letter 1D465 minus 6, each have a slope of 2, they represent parallel lines. Perpendicular lines have negative reciprocal slopes. Because minus 2 and 12 are negative reciprocals, the functions letter 1D454, letter 1D465 equals 12 letter 1D465 minus 4, and letter 210e, letter 1D465 equals minus 2 letter 1D465 plus 2, represent perpendicular lines. Analysis. A graph of the lines is shown in figure 30. This graph shows 4 functions on an x, y coordinate plane. The x-axis runs from -8 to 9. The y-axis runs from -8 to 8. The first shows the decreasing function h of x equals -2 times x plus 2. It passes through the points 0, 2, and 1, 0. The second is an increasing function that shows f of x equals 2 times x plus 3. It passes through the points 0, 3, and -1, 5, 0. The third is an increasing function that shows j of x equals 2 times x minus 6 and passes through the points 0, -6, and 3, 0. The fourth line is an increasing function where g of x equals x divided by 2 minus 4 and passes through the points 0, -4, and 2, 0. Figure 30. The graph shows that the lines letter 1d453, letter 1d465 equals 2 letter 1d465 plus 3, and letter 1d457, letter 1d465 equals 2 letter 1d465 6 are parallel, and the lines letter 1d454, letter 1d465 equals 12 letter 1d465 4, and letter 210e, letter 1d465 equals -2 letter 1d465 plus 2 are perpendicular, writing the equation of a line parallel or perpendicular to a given line. If we know the equation of a line, we can use what we know about slope to write the equation of a line that is either parallel or perpendicular to the given line. Writing equations of parallel lines. Suppose, for example, we are given the equation shown. Letter 1d453, letter 1d465 equals 3 letter 1d465 plus 1. We know that the slope of the line formed by the function is 3. We also know that the y-intercept is 1. Any other line with a slope of 3 will be parallel to letter 1d453, letter 1d465. So the lines formed by all of the following functions will be parallel to letter 1d453, letter 1d465, letter 1d454, letter 1d465, letter 210e, letter 1d465, letter 1d45d, letter 1d465, equals 3 letter 1d465 plus 63 letter 1d465 plus 13 letter 1d465 plus 23. Suppose, then, we want to write the equation of a line that is parallel to letter 1d453 and passes through the point 1, 7. This type of problem is often described as a point-slope problem because we have a point and a slope. In our example, we know that the slope is 3. We need to determine which value of letter 1d44f will give the correct line. We can begin with the point-slope form of an equation for a line, and then rewrite it in the slope-intercept form. Letter 1d466 minus letter 1d466, 1 letter 1d466 minus 7 letter 1d466 minus 7 letter 1d466 equals letter 1d45a. Letter 1d465 minus letter 1d465 1 3. Letter 1d465 minus 1 3 letter 1d465 minus 33 letter 1d465 plus 4. So letter 1d454, letter 1d465 equals 3 letter 1d465 plus 4 is parallel to letter 1d453. Letter 1d465 equals 3 letter 1d465 plus 1 and passes through the point 1, 7. How to, given the equation of a function and a point through which its graph passes, write the equation of a line parallel to the given line that passes through the given point. Find the slope of the function. Substitute the given values into either the general point-slope equation or the slope-intercept equation for a line. Simplify. Example 19. Finding a line parallel to a given line. Find a line parallel to the graph of letter 1d453, letter 1d465, equals 3 letter 1d465 plus 6. That passes through the point 30. Solution. The slope of the given line is 3. If we choose the slope-intercept form, we can substitute letter 1d45a equals 3, letter 1d465 equals 3, and letter 1d453, letter 1d465 equals 0 into the slope-intercept form to find the y-intercept. Letter 1d454, letter 1d465 0, letter 1d44f equals 3 letter 1d465 plus letter 1d44f 3, 3, plus letter 1d44f 9. The line parallel to letter 1d453, letter 1d465, that passes through 3, 0, is letter 1d454, letter 1d465 equals 3 letter 1d465 minus 9. Analysis. We can confirm that the two lines are parallel by graphing them. Figure 31 shows that the two lines will never intersect. This is a graph of two functions on an x, y coordinate plane. The x-axis runs from -6 to 6, and the y-axis runs from -2 to 10. The first function is y equals 3 times x plus 6. On this line is the point at 0, 6, with an arrow extending right 1 unit labeled right 1. From here, the arrow extends upward 3 units labeled up 3. The next function is y equals 3 times x minus 9. On this line is the point 3, 0 with an arrow extending right 1 unit labeled right 1. From here is an arrow extending upward 3 units labeled up 3. Figure 31. Writing equations of perpendicular lines. We can use a very similar process to write the equation for a line perpendicular to a given line. Instead of using the same slope, however, we use the negative reciprocal of the given slope. Suppose we are given the function shown. Letter 1d453, letter 1d465 equals 2 letter 1d465 plus 4. The slope of the line is 2, and its negative reciprocal is minus 12. Any function with a slope of minus 12 will be perpendicular to letter 1d453, letter 1d465. So the lines formed by all of the following functions will be perpendicular to letter 1d453, letter 1d465, letter 1d454, letter 1d465, letter 210e, letter 1d465, letter 1d45d, letter 1d465, equals minus 12 letter 1d465 plus 4 minus 12 letter 1d465 plus 2 minus 12 letter 1d465 minus 12. As before, we can narrow down our choices for a particular perpendicular line if we know that it passes through a given point. Suppose then we want to write the equation of a line that is perpendicular to letter 1d453, letter 1d465, and passes through the point 40. We already know that the slope is minus 12. Now we can use the point to find the y-intercept by substituting the given values into the slope-intercept form of a line and solving for letter 1d44f. Letter 1d454, letter 1d465 0, 0, 2 letter 1d44f equals letter 1d45a letter 1d465 plus letter 1d44f minus 12, 4, plus letter 1d44f minus 2 plus letter 1d44f letter 1d44f 2. The equation for the function with a slope of minus 12 and a y-intercept of 2 is letter 1d454, letter 1d465 equals minus 12 letter 1d465 plus 2. So letter 1d454, letter 1d465 equals minus 12 letter 1d465 plus 2 is perpendicular to letter 1d453, letter 1d465 equals 2 letter 1d465 plus 4, and passes through the point 4, 0. Be aware that perpendicular lines may not look obviously perpendicular on a graphing calculator unless we use the square zoom feature. Q and A. A horizontal line has a slope of 0, and a vertical line has an undefined slope. These two lines are perpendicular, but the product of their slopes is not 1. Doesn't this fact contradict the definition of perpendicular lines? No. For two perpendicular linear functions, the product of their slopes is 1. However, a vertical line is not a function, so the definition is not contradicted. How to given the equation of a function and a point through which its graph passes, write the equation of a line perpendicular to the given line. Find the slope of the function. Determine the negative reciprocal of the slope. Substitute the new slope and the values for x and y from the coordinate pair provided into letter 1d454. Letter 1d465 equals letter 1d45a letter 1d465 plus letter 1d44f. Solve for B. Write the equation of the line. Example 20. Finding the equation of a perpendicular line. Find the equation of a line perpendicular to letter 1d453, letter 1d465, equals 3 letter 1d465 plus 3 that passes through the point 30. Solution. The original line has slope letter 1d45a equals 3. So the slope of the perpendicular line will be its negative reciprocal, or minus 13. Using this slope and the given point, we can find the equation of the line. The line perpendicular to letter 1d453, letter 1d465, that passes through 3, 0 is letter 1d454, letter 1d465 equals minus 13 letter 1d465 plus 1. Analysis: a graph of the two lines is shown in figure 32. This is a graph of two functions on an x, y coordinate plane. The x-axis runs from -6 to 6. The y-axis runs from -4 to 10. The first function shows g of x equals -x divided by 3 plus 1. The second function shows f of x equals 3 times x plus 6. The lines intersect at the point -1, 5, 1, 5 to form a 90-degree right angle. Figure 32 note that if we graph perpendicular lines on a graphing calculator using standard zoom, the lines may not appear to be perpendicular. Adjusting the window will make it possible to zoom in further to see the intersection more closely. Try at 9 given the function letter 210e. Letter 1d465 equals 2 letter 1d465 minus 4. Write an equation for the line passing through 0. 0, that is A parallel to letter 210e. Letter 1d465. Be perpendicular to letter 210e. Letter 1d465. How to given 2 points on a line and a third point. Write the equation of the perpendicular line that passes through the point. Determine the slope of the line passing through the points. Find the negative reciprocal of the slope. Use the slope-intercept form or point-slope form to write the equation by substituting the known values. Simplify. Example 21, finding the equation of a line perpendicular to a given line passing through a point A. Line passes through the points -2, 6, and 45. Find the equation of a perpendicular line that passes through the point 45. Solution: from the 2 points of the given line, we can calculate the slope of that line. Find the negative reciprocal of the slope. Letter 1d45a2 equals minus 1 minus 16 minus 1 minus 61. 6. We can then solve for the y-intercept of the line passing through the point 45. Letter 1d454. Letter 1d465. 55 minus 19 letter 1d44f equals 6 letter 1d465 plus letter 1d44f 6. 4. Plus letter 1d44f 24 plus letter 1d44f letter 1d44f minus 19. The equation for the line that is perpendicular to the line passing through the two given points and also passes through point 4. 5 is letter 1d466 equals 6 letter 1d465 minus 19. Try it 10. A line passes through the points -2, -15, and 2, -3. Find the equation of a perpendicular line that passes through the point 64. Media access this online resource for additional instruction and practice with linear functions. Linear functions: finding input of function from the output and graphing functions using tables 4. 1 section exercises verbal 1. Terry is skiing down a steep hill. Terry's elevation, letter 1d438, letter 1d461, in feet after t seconds is given by letter 1d438, letter 1d461, equals 3000 minus 70 letter 1d461. Write a complete sentence describing Terry's starting elevation and how it is changing over time. 2. Jessica is walking home from a friend's house. After 2 minutes, she is 4 miles from home. 12 minutes after leaving, she is 9 miles from home. What is her rate in miles per hour? 3. A boat is 100 miles away from the marina, sailing directly toward it at 10 miles per hour. Write an equation for the distance of the boat from the marina after t hours. 4. If the graphs of two linear functions are perpendicular, describe the relationship between the slopes and the y-intercepts. 5. If a horizontal line has the equation letter 1d453, letter 1d465 equals letter 1d44e, and a vertical line has the equation letter 1d465 equals letter 1d44e, what is the point of intersection? Explain why what you found is the point of intersection. Algebraic for the following exercises, determine whether the equation of the curve can be written as a linear function. 6. Letter 1d466 equals 14 letter 1d465 plus 6, 7. Letter 1d466 equals 3 letter 1d465 minus 5, 8. Letter 1d466 equals 3 letter 1d465 2 minus 2, 9. 3 letter 1d465 plus 5 letter 1d466 equals 15, 10. 3 letter 1d465 2 plus 5 letter 1d466 equals 1511. 3 letter 1d465 plus 5 letter 1d466 2 equals 1512. Minus 2 letter 1d465 2 plus 3 letter 1d466 2 equals 613. Minus letter 1d465 minus 35 equals 2 letter 1d466 for the following exercises. Determine whether each function is increasing or decreasing. 14. Letter 1d453, letter 1d465 equals 4 letter 1d465 plus 315. Letter 1d454, letter 1d465 equals 5 letter 1d465 plus 616. Letter 1d440, letter 1d465 equals 5 minus 2 letter 1d465 17. Letter 1d44f, letter 1d465 equals 8 minus 3 letter 1d465 18. Letter 210e, letter 1d465 equals minus 2 letter 1d465 plus 419. Letter 1d458, letter 1d465 equals minus 4 letter 1d465 plus 120. Letter 1d457, letter 1d465 equals 12 letter 1d465 minus 321. Letter 1d45d, letter 1d465 equals 14 letter 1d465 minus 522. Letter 1d45b, letter 1d465 equals minus 13 letter 1d465 minus 223. Letter 1d45a, letter 1d465 equals minus 38 letter 1d465 plus 3 for the following exercises. Find the slope of the line that passes through the two given points. 24, 24 and 410, 25. 15 and 411, 26. 14 and 52, 27. 8, 2 and 46, 28. 611 and 43 for the following exercises. Given each set of information, find a linear equation satisfying the conditions if possible. 29. Letter 1d453, minus 5 equals minus 4, and letter 1d453, 5 equals 230. Letter 1d453, minus 1 equals 4, and letter 1d453, 5 equals 131. Passes through 24 and 410, 32. Passes through 15 and 411, 33. Passes through minus 1, 4 and 52, 34. Passes through minus 2, 8 and 46, 35. X-intercept at minus 2, 0, and y-intercept at 0, minus 3, 36. X-intercept at minus 5, 0, and y-intercept at 4 for the following exercises. Determine whether the lines given by the equations below are parallel, perpendicular, or neither. 37. 4 letter 1d465 minus 7 letter 1d466 equals 107 letter 1d465 plus 4 letter 1d466 equals 138. 3 letter 1d466 plus letter 1d465 equals 12 minus letter 1d466 equals 8 letter 1d465 plus 139. 3 letter 1d466 plus 4 letter 1d465 equals 12 minus 6 letter 1d466 equals 8 letter 1d465 plus 140. 6 letter 1d465 minus 9 letter 1d466 equals 103 letter 1d465 plus 2 letter 1d466 equals 1 for the following exercises. Find the x and y-intercepts of each equation. 41. Letter 1d453, letter 1d465 equals minus letter 1d465 plus 242. Letter 1d454, letter 1d465 equals 2 letter 1d465 plus 443. Letter 210e, letter 1d465 equals 3 letter 1d465 minus 544. Letter 1d458, letter 1d465 equals minus 5 letter 1d465 plus 145. Minus 2 letter 1d465 plus 5 letter 1d466 equals 2046. 7 letter 1d465 plus 2 letter 1d466 equals 56 for the following exercises. Use the descriptions of each pair of lines given below to find the slopes of line 1 and line 2. Is each pair of lines parallel, perpendicular, or neither? 47. Line 1 passes through 6 and 3, minus 24. Line 2 passes through minus 1, 19, and 8, minus 71, 48. Line 1 passes through -8 -55 and 1089. Line 2 passes through 9 -44 and 4 -1449. Line 1 passes through 23 and 4 -1. Line 2 passes through 63 and 8550. Line 1 passes through 17 and 55. Line 2 passes through -1 -3 and 1151. Line 1 passes through 25 and 5 -1. Line 2 passes through -3 7 and 3 -5. For the following exercises, write an equation for the line described. 52. Write an equation for a line parallel to letter 1D453, letter 1D465, equals -5 letter 1D465 -3, and passing through the point 2, 12. 53. Write an equation for a line parallel to letter 1D454, letter 1D465, equals 3 letter 1D465 -1, and passing through the point 49. 54. Write an equation for a line perpendicular to letter 210e, letter 1D461, equals -2 letter 1D461 plus 4, and passing through the point -4, 1. 55. Write an equation for a line perpendicular to letter 1D45d, letter 1D461 equals 3 letter 1D461 plus 4, and passing through the point 31. Graphical for the following exercises, find the slope of the line graphed. 56. This is a graph of a decreasing linear function on an x, y coordinate plane. The x-axis runs from -6 to 6. The y-axis runs from -6 to 6. The line passes through points 0, 5, and 4, 0. 57. This is a graph of a function on an x, y coordinate plane. The x-axis runs from -6 to 6. The y-axis runs from -6 to 6. The lines passes through points at 0, -2, and 2, -2. For the following exercises, write an equation for the line graphed. 58. Graph of an increasing linear function with points at 1 and 33, 59. Graph of a decreasing linear function with points 5 and 40, 60. Graph of a decreasing linear function with points at 3 and 150, 61. Graph of an increasing linear function with points at 12 and 0, 62. Graph of a function with points at 0, 3, and 3, 63. Graph of a function with points at 0, 5, and -2, 5. 5. For the following exercises, match the given linear equation with its graph in figure 33. Graph of 6 functions where line A has a slope of 3 and y-intercept at 2, line B has a slope of 1 and y-intercept at 2, line C has a slope of 0 and y-intercept at 2, line D has a slope of -1, 2 and y-intercept at -1, line E has a slope of -1 and y-intercept at -1, and line F has a slope of -2 and y-intercept at -1. Figure 30, 364. Letter 1D453, letter 1D465, equals minus letter 1D465 minus 165. Letter 1D453, letter 1D465, equals minus 3 letter 1D465 minus 166. Letter 1D453, letter 1D465, equals minus 12 letter 1D465 minus 167. Letter 1D453, letter 1D465 equals 268. Letter 1D453, letter 1D465 equals 2 plus letter 1D465 69. Letter 1D453, letter 1D465 equals 3 letter 1D465 plus 2. For the following exercises, sketch a line with the given features. 70, an x-intercept of 40 and y-intercept of 0, 2, 71. An x-intercept 20 and y-intercept of 4, 72. A y-intercept of 7 and slope minus 30, 73. A y-intercept of 3 and slope 25, 74. Passing through the points 6, 2 and 6, 6, 75. Passing through the points 3, 4 and 30. For the following exercises, sketch the graph of each equation. 76. Letter 1D453, letter 1D465 equals minus 2 letter 1D465 minus 177. Letter 1D453, letter 1D465 equals minus 3 letter 1D465 plus 278. Letter 1D453, letter 1D465 equals 13 letter 1D465 plus 279. Letter 1d453, letter 1d465, equals 23 letter 1d465 minus 380. Letter 1d453, letter 1d461, equals 3 plus 2 letter 1d461 81. Letter 1d45d, letter 1d461, equals minus 2 plus 3 letter 1d461 82. Letter 1d465 equals 383. Letter 1d465 equals minus 284. Letter 1d45f, letter 1d465, equals 4 for the following exercises. Write the equation of the line shown in the graph. 85. The graph of a line with a slope of 0 and y-intercept at 386. Graph of a line with a slope of 0 and y-intercept at minus 1. 87. Graph of a line with an undefined slope and x-intercept at 88. Graph of a line with an undefined slope and x-intercept at 2 numeric for the following exercises. Which of the tables could represent a linear function? For each that could be linear, find a linear equation that models the data. 89. x0, 5, 10, 15, letter 1d454, letter 1d465, 5, 10, 25, 40, 90. x0, 5, 10, 15, letter 210e, letter 1d465, 5, 30, 105, 230, 91. x0, 5, 10, 15, letter 1d453, letter 1d465, 5, 20, 40, 5, 70, 92. x5, 10, 20, 25, letter 1d458, letter 1d465, 13, 28, 58, 73, 93. x0, 2, 4, 6, letter 1d454, letter 1d465, 6, 19, 44, 69, 94. x2, 4, 8, 10, letter 210e, letter 1d465, 13, 23, 43, 53, 95. x2, 4, 6, 8, letter 1d453, letter 1d465, 4, 16, 36, 56, 96. x0, 2, 6, 8, letter 1d458, letter 1d465, 6, 31, 106, 231. Technology. For the following exercises, use a calculator or graphing technology to complete the task. 97. If f is a linear function, letter 1d453, 0, 1 equals 11, 5, and letter 1d453, 0, 4 equals 5. 9. Find an equation for the function. 98. Graph the function f on a domain of 1010, letter 1d453, letter 1d465, equals 0. 0, 2, letter 1d465 minus 0. 1. Enter the function in a graphing utility. For the viewing window, set the minimum value of x to be minus 10 and the maximum value of x to be 10. 99. Graph the function f on a domain of 1010. Letter 1d453, letter 1d465 equals 2, 500, letter 1d465 plus 4, 0, 0, 0, 100. Table 3 shows the input, w, and output, k. For a linear function k, a, fill in the missing values of the table. B, write the linear function k, round to 3 decimal places. W, 10, 5, 5, 67, 5b, k, 30, 26 of 44. Table 3, 101. Table 4 shows the input, p, and output, q. For a linear function q, a, fill in the missing values of the table. B, write the linear function kp0, 50. 812 bq 400 700, a 1 million. Table 4, 102. Graph the linear function f on a domain of minus 10, 10, for the function whose slope is 18 and y-intercept is 30, 116. Label the points for the input values of minus 10 and 10. 103. Graph the linear function f on a domain of minus 0. 10. 1 for the function whose slope is 75 and y-intercept is minus 22. 5. Label the points for the input values of minus 0. 1 and 0, 1, 104. Graph the linear function f where letter 1d453, letter 1d465, equals letter 1d44, letter 1d465, plus letter 1d44f on the same set of axes on a domain of minus 4. 4 for the following values of a and b. A, letter 1d44e equals 2. Letter 1d44f equals 3. B, letter 1d44e equals 2. Letter 1d44f equals 4. C, letter 1d44e equals 2. Letter 1D44F equals 4D. Letter 1D44E equals 2. Letter 1D44F equals 5 extensions 105. Find the value of x if a linear function goes through the following points and has the following slope. Letter 1D4652 minus 4, 6. Letter 1D45A equals 3, 106. Find the value of y if a linear function goes through the following points and has the following slope. 10. Letter 1D466, 25, 100. Letter 1D45A equals minus 5, 107. Find the equation of the line that passes through the following points. AB and AB plus 1, 108. Find the equation of the line that passes through the following points. 2AB and AB plus 1, 109. Find the equation of the line that passes through the following points. A0 and CD, 110. Find the equation of the line parallel to the line letter 1D454, letter 1D465 equals minus 0. 1x plus 2, 1 through the point 12, 111. Find the equation of the line perpendicular to the line letter 1D454, letter 1D465 equals minus 0. 1x plus 2, 1 through the point 12. For the following exercises, use the functions letter 1D453, letter 1D465 equals minus 0. 1x plus 200 and letter 1D454, letter 1D465 equals 20. Letter 1D465 plus 0. 112. Find the point of intersection of the lines F and G. 113. Where is letter 1D453, letter 1D465, greater than letter 1D454, letter 1D465? Where is letter 1D454, letter 1D465, greater than letter 1D453, letter 1D465? Real-world applications 114. At noon, a barista notices that they have $20 in their tip jar. If the barista makes an average of $0, $50 from each customer, how much will they have in the tip jar if they serve n more customers during the shift? 115. A gym membership with 2 personal training sessions costs $125, while gym membership with 5 personal training sessions costs $260. What is cost per session? 116. A clothing business finds there is a linear relationship between the number of shirts, N, it can sell, and the price, P, it can charge per shirt. In particular, historical data shows that 1,000 shirts can be sold at a price of $30, while 3,000 shirts can be sold at a price of $22. Find a linear equation in the form letter 1D45D. Letter 1D45B equals letter 1D45A letter 1D45B plus letter 1D44F that gives the price P they can charge for N shirts. 117. A phone company charges for service according to the formula letter 1D436, letter 1D45B equals 24 plus 0. 1N, where N is the number of minutes talked, and letter 1D436, letter 1D45B is the monthly charge in dollars. Find and interpret the rate of change and initial value. 118. A farmer finds there is a linear relationship between the number of beanstalks, N, she plants, and the yield, Y, each plant produces. When she plants 30 stalks, each plant yields 30 ahs of beans. When she plants 34 stalks, each plant produces 28 ahs of beans. Find a linear relationships in the form letter 1D466 equals letter 1D45A letter 1D45B plus letter 1D44F that gives the yield when N stalks are planted. 119. A city's population in the year 1960 was 287,500. In 1989, the population was 275,900. Compute the rate of growth of the population and make a statement about the population rate of change in people per year. 120. A town's population has been growing linearly. In 2003, the population was 45,000, and the population has been growing by 1,700 people each year. Write an equation, letter 1D443, letter 1D461, for the population T years after 2003. 121. Suppose that average annual income in dollars for the years 1990 through 1999 is given by the linear function. Letter 1D43C, letter 1D465, equals 1054 letter 1d465 plus 23,286, where x is the number of years after 1990. Which of the following interprets the slope in the context of the problem? As of 1990, average annual income was $23,286. B. In the 10-year period from 1990 to 1999, average annual income increased by a total of $1,054. C. Each year in the decade of the 1990s, average annual income increased by $1,054. D. Average annual income rose to a level of $23,286 by the end of 1999. 122. When temperature is 0 degrees Celsius, the Fahrenheit temperature is 32. When the Celsius temperature is 100, the corresponding Fahrenheit temperature is 212. Express the Fahrenheit temperature as a linear function of C, the Celsius temperature, letter 1d439, letter 1d436. A. Find the rate of change of Fahrenheit temperature for each unit change temperature of Celsius. B. Find and interpret letter 1d439, 28. C. Find and interpret letter 1d439, 40. Learning objectives. In this section, you will build linear models from verbal descriptions, model a set of data with a linear function, a skyline view of Seattle with a focus on the Space Needle. Figure 1, credit. Eek photography/Flickr. Elan is a college student who plans to spend a summer in Seattle. Elan has saved $3,500 for their trip and anticipates spending $400 each week on rent, food, and activities. How can we write a linear model to represent this situation? What would be the x-intercept, and what can Elan learn from it? To answer these and related questions, we can create a model using a linear function. Models such as this one can be extremely useful for analyzing relationships and making predictions based on those relationships. In this section, we will explore examples of linear function models. Building linear models from verbal descriptions. When building linear models to solve problems involving quantities with a constant rate of change, we typically follow the same problem strategies that we would use for any type of function. Let's briefly review them. Identify changing quantities, and then define descriptive variables to represent those quantities. When appropriate, sketch a picture or define a coordinate system. Carefully read the problem to identify important information. Look for information that provides values for the variables or values for parts of the functional model, such as slope and initial value. Carefully read the problem to determine what we are trying to find, identify, solve, or interpret. Identify a solution pathway from the provided information to what we are trying to find. Often this will involve checking and tracking units, building a table, or even finding a formula for the function being used to model the problem. When needed, write a formula for the function. Solve or evaluate the function using the formula. Reflect on whether your answer is reasonable for the given situation and whether it makes sense mathematically. Clearly convey your result using appropriate units and answer in full sentences when necessary. Now let's take a look at the student in Seattle. In Elan's situation, there are two changing quantities, time and money. The amount of money they have remaining while on vacation depends on how long they stay. We can use this information to define our variables, including units. Output, money remaining in dollars input, time in weeks. So, the amount of money remaining depends on the number of weeks. Letter 1d440, letter 1d461. We can also identify the initial value and the rate of change. Initial value. She saved $3,500, so $3,500 is the initial value for M. Rate of change. She anticipates spending $400 each week, so minus $400 per week is the rate of change, or slope. Notice that the unit of dollars per week matches the unit of our output variable divided by our input variable. Also, because the slope is negative, the linear function is decreasing. This should make sense because she is spending money each week. The rate of change is constant, so we can start with the linear model letter 1d440, letter 1d461, equals letter 1d45a, letter 1d461, plus letter 1d44f. Then we can substitute the intercept and slope provided. To find the t-intercept, horizontal axis intercept, We set the output to 0 and solve for the input. 0 letter 1d461 equals minus 400 letter 1d461 plus 350 billion 30 5,004,008. 75. The t-intercept, horizontal axis intercept, is 875 weeks. Because this represents the input value when the output will be 0, we could say that Elon will have no money left after 875 weeks. When modeling any real-life scenario with functions, there is typically a limited domain over which that model will be valid. Almost no trend continues indefinitely. Here the domain refers to the number of weeks. In this case, it doesn't make sense to talk about input values less than 0. A negative input value could refer to a number of weeks before Elon saved $3,500, but the scenario discussed poses the question once they saved $3,500, because this is when the trip and subsequent spending starts. It is also likely that this model is not valid after the t-intercept, horizontal axis intercept, unless Elon uses a credit card and goes into debt. The domain represents the set of input values, so the reasonable domain for this function is 0 less or equal to letter 1d461 less or equal to 875. In this example, we were given a written description of the situation. We followed the steps of modeling a problem to analyze the information. However, the information provided may not always be the same. Sometimes we might be provided with an intercept. Other times we might be provided with an output value. We must be careful to analyze the information we are given and use it appropriately to build a linear model. Using a given intercept to build a model. Some real-world problems provide the vertical axis intercept, which is the constant or initial value. Once the vertical axis intercept is known, the t-intercept, horizontal axis intercept, can be calculated. Suppose, for example, that Hannah plans to pay off a no-interest loan from her parents. Her loan balance is $1,000. She plans to pay $250 per month until her balance is $0. The y-intercept is the initial amount of her debt, or $1,000. The rate of change, or slope, is $250 per month. We can then use the slope-intercept form and the given information to develop a linear model. Letter 1d453, letter 1d465, equals letter 1d45a letter 1d465, plus letter 1d44f minus 250 letter 1d465 plus 1,000. Now we can set the function equal to 0 and solve for letter 1d465. To find the x-intercept, 010,004 letter 1d465 equals minus 250 letter 1d465 plus 1,250 letter 1d465 letter 1d465 4. The x-intercept is the number of months it takes her to reach a balance of $0. The x-intercept is 4 months, so it will take Hannah 4 months to pay off her loan. Using a given input and output to build a model. Many real-world applications are not as direct as the ones we just considered. Instead, they require us to identify some aspect of a linear function. We might sometimes instead be asked to evaluate the linear model at a given input or set the equation of the linear model equal to a specified output. How to? Given a word problem that includes 2 pairs of input and output values, use the linear function to solve a problem. Identify the input and output values. Convert the data to 2 coordinate pairs. Find the slope. Write the linear model. Use the model to make a prediction by evaluating the function at a given x value. Use the model to identify an x value that results in a given y value. Answer the question posed. Example 1. Using a linear model to investigate a town's population. A town's population has been growing linearly. In 2004, the population was 6,200. By 2009, the population had grown to 8,100. Assume this trend continues. Predict the population in 2013. B. Identify the year in which the population will reach 15,000. Solution. The 2 changing quantities are the population size and time, while we could use the actual year value as the input quantity. Doing so tends to lead to very cumbersome equations because the y-intercept would correspond to the year 0, more than 2,000 years ago. To make computation a little nicer, we will define our input as the number of years since 2004. Input, T years since 2004. Output, letter 1D443, letter 1D461, the town's population. To predict the population in 2013, we would first need an equation for the population. Likewise, to find when the population would reach 15,000, we would need to solve for the input that would provide an output of 15,000. To write an equation, we need the initial value and the rate of change, or slope. To determine the rate of change, we will use the change in output per change in input. Letter 1D45A equals change in output change in input. The problem gives us two input-output pairs. Converting them to match our defined variables, the year 2004 would correspond to letter 1D461 equals 0, giving the point 6,200. Notice that through our clever choice of variable definition, we have given ourselves the y-intercept of the function. The year 2009 would correspond to letter 1D461 equals 5, giving the point 58,100. The two coordinate pairs are 6,200 and 58,100. Recall that we encountered examples in which we were provided 2 points earlier in the chapter. We can use these values to calculate the slope. Letter 1D45A equals 8,100 minus 62,005 minus 019,005,380 people per year. We already know the y-intercept of the line, so we can immediately write the equation. Letter 1D443. Letter 1D461 equals 380 letter 1D461 plus 6,200. To predict the population in 2013, we evaluate our function at letter 1D461 equals 9. Letter 1D443, 9 equals 389 plus 6, 2009, 620. If the trend continues, our model predicts a population of 9,620 in 2013. To find when the population will reach 15,000, we can set letter 1D443, letter 1D461 equals 15,000, and solve for letter 1D461. 150,008,800 letter 1D461 equals approximately 380 letter 1D461 plus 6,200,380 letter 1D461, 23. 158. Our model predicts the population will reach 15,000 in a little more than 23 years after 2004, or somewhere around the year 2027. Try it 1. A company sells donuts. They incur a fixed cost of $25,000 for rent, insurance, and other expenses. It costs $0, $25 to produce each donut. Write a linear model to represent the cost, letter 1D436, of the company as a function of letter 1D465, the number of donuts produced. Find and interpret the y-intercept. Try it 2. A city's population has been growing linearly. In 2008, the population was 28,200. By 2012, the population was 36,800. Assume this trend continues. Predict the population in 2014. Identify the year in which the population will reach 54,000. Using a diagram to build a model. It is useful for many real-world applications to draw a picture to gain a sense of how the variables representing the input and output may be used to answer a question. To draw the picture, first consider what the problem is asking for. Then, determine the input and the output. The diagram should relate the variables. Often, geometrical shapes or figures are drawn. Distances are often traced out. If a right triangle is sketched, the Pythagorean theorem relates the sides. If a rectangle is sketched, labeling width and height is helpful. Example 2. Using a diagram to model distance walked. Anna and Emmanuel start at the same intersection. Anna walks east at 4 miles per hour, while Emmanuel walks south at 3 miles per hour. They are communicating with a two-way radio that has a range of 2 miles. How long after they start walking will they fall out of radio contact? Solution. In essence, we can partially answer this question by saying they will fall out of radio contact when they are 2 miles apart, which leads us to ask a new question. How long will it take them to be 2 miles apart? In this problem, our changing quantities are time and position, but ultimately we need to know how long will it take for them to be 2 miles apart. We can see that time will be our input variable, so we'll define our input and output variables. Input, t time in hours. Output, letter 1 D434, letter 1 D461, distance in miles, and letter 1 D438, letter 1 D461, distance in miles. Because it is not obvious how to define our output variable, we'll start by drawing a picture such as figure 2. Emmanuel is walking south at 3 miles an hour, while Anna is walking east at 4 miles an hour. The image shows a dotted, diagonal line that is labeled as the distance between them. Figure 2. Initial value. They both start at the same intersection, so when letter 1 D461 equals 0, the distance traveled by each person should also be 0, thus the initial value for each is 0. Rate of change. Anna is walking 4 miles per hour and Emmanuel is walking 3 miles per hour, which are both rates of change. The slope for letter 1 D434 is 4 and the slope for letter 1 D438 is 3. Using those values, we can write formulas for the distance each person has walked. Letter 1 D434, letter 1 D461, letter 1 D438, letter 1 D461 equals 4 letter 1 D461, 3 letter 1 D461. For this problem, the distances from the starting point are important. To notate these, we can define a coordinate system, identifying the starting point at the intersection where they both started. Then we can use the variable letter 1 D434, which we introduced above, to represent Anna's position and define it to be a measurement from the starting point in the eastward direction. Likewise, can use the variable letter 1 D438 to represent Emmanuel's position, measured from the starting point in the southward direction. Note that in defining the coordinate system, we specified both the starting point of the measurement and the direction of measure. We can then define a third variable, letter 1 D437, to be the measurement of the distance between Anna and Emmanuel. Showing the variables on the diagram is often helpful, as we can see from figure 3. Recall that we need to know how long it takes for letter 1 D437, the distance between them, to equal 2 miles. Notice that for any given input letter 1 D461, the outputs letter 1 D434, letter 1 D461, letter 1 D438, letter 1 D461, and represent distances. The rate of change of Emmanuel and Anna where the rise of the slope is labeled E, the run is labeled A, and the hypotenuse is labeled D. The lines EAD form a right triangle. Figure 3. Figure 2 shows us that we can use the Pythagorean theorem because we have drawn a right angle. Using the Pythagorean theorem, we get letter 1 D437, letter 1 D4612, letter 1 D437, letter 1 D461 equals letter 1 D434, letter 1 D4612 plus letter 1 D438, letter 1 D4612, 4 letter 1 D4612 plus 3 letter 1 D461 216, letter 1 D4612 plus 9 letter 1 D461 225, letter 1 D461 2 plus or minus 25. For letter 1 D437, letter 1 D461, using the square root. In this scenario, we are considering only positive values of letter 1 D461. So our distance, letter 1 D437, letter 1 D461, will always be positive. We can simplify this answer to letter 1 D437, letter 1 D461, equals 5 letter 1 D461. This means that the distance between Anna and Emmanuel is also a linear function. Because letter 1 D437 is a linear function, we can now answer the question of when the distance between them will reach 2 miles. We will set the output letter 1 D437, letter 1 D461 equals 2, and solve for letter 1 D461, letter 1 D437, letter 1 D461, 5 letter 1 D461, letter 1 D461 equals 2,225 equals 0. 4. They will fall out of radio contact in 0. 4 hour or 24 minutes, Q&A. Should I draw diagrams when given information based on a geometric shape? Yes. Sketch the figure and label the quantities and unknowns on the sketch. Example 3. Using a diagram to model distance between cities. There is a straight road leading from the town of Westboro to Agrietown 30 miles east and 10 miles north. Partway down this road, it junctions with a second road, perpendicular to the first, leading to the town of Eastboro. If the town of Eastboro is located 20 miles directly east of the town of Westboro, How far is the road junction from Westboro? Solution. It might help here to draw a picture of the situation. See Figure 4. It would then be helpful to introduce a coordinate system. While we could place the origin anywhere, placing it at Westboro seems convenient. This puts Agrietown at coordinates 3010 and Eastboro at 200. Graph of the intersection of the three roads, Westboro, Eastboro, and Agrietown. Westboro is at the point 0 and Eastboro is 20 miles east at the point 200. Agrietown is at the point 3010 with a line connecting Westboro to Agrietown. A line perpendicular to the previously mentioned line extends from Eastboro. Figure 4. Using this point along with the origin, we can find the slope of the line from Westboro to Agrietown. Letter 1D45A equals 10 minus 0, 30 minus 0 equals 13. Now we can write an equation to describe the road from Westboro to Agrietown. Letter 1D44A, letter 1D465 equals 13 letter 1D465. From this, we can determine the perpendicular road to Eastboro will have slope letter 1D45A equals 3. Because the town of Eastboro is at the point 20, 0, we can find the equation. Letter 1D438, letter 1D465, 0, letter 1D44F, letter 1D438, letter 1D465 equals minus 3 letter 1D465 plus letter 1D44F minus 3, 20. Plus letter 1D44F, 60 minus 3 letter 1D465 plus 60 substitute, 20, 0 into the equation. We can now find the coordinates of the junction of the roads by finding the intersection of these lines. Setting them equal, 13x1, 03x10, letter 1D465, letter 1D465, letter 1D466 equals minus 3 letter 1D465 plus 606,018,018 letter 1D44A. 1813. 18. 6. Substitute this back into letter 1D44A, letter 1D465. The roads intersect at the point 18, 6. Using the distance formula, we can now find the distance from Westboro to the junction. Distance equals approximately letter 1D465 2 minus letter 1D465 1 2 plus letter 1D466 2 minus letter 1D466 1 2 square 18 minus 0 2 plus 6 minus 0, 2 square 18. 974 miles. Analysis. One nice use of linear models is to take advantage of the fact that the graphs of these functions are lines. This means real-world applications discussing maps need linear functions to model the distances between reference points. Try it 3. There is a straight road leading from the town of Timpson to Ashburn 60 miles east and 12 miles north. Partway down the road, it junctions with a second road, perpendicular to the first, leading to the town of Garrison. If the town of Garrison is located 22 miles directly east of the town of Timpson, how far is the road junction from Timpson? Modeling a set of data with linear functions. Real-world situations, including 2 or more linear functions, may be modeled with a system of linear equations. Remember, when solving a system of linear equations, we are looking for points the two lines have in common. Typically, there are 3 types of answers possible, as shown in Figure 5. The graph in A is of 2 intersecting lines. The point of intersection is marked and labeled, exactly one solution. Figure B shows one line and is labeled, infinitely many solutions. Figure C shows 2 parallel lines labeled, no solutions. Figure 5. How to. Given a situation that represents a system of linear equations, write the system of equations and identify the solution. Identify the input and output of each linear model. Identify the slope and y-intercept of each linear model. Find the solution by setting the 2 linear functions equal to another and solving for letter 1D465, or find the point of intersection on a graph. Example 4. Building a system of linear models to choose a truck rental company. Jamal is choosing between 2 truck rental companies. The first, Keep on Trucking, Inc., charges an upfront fee of $20, then 59 cents a mile. The second, Move It Your Way, charges an upfront fee of $16, then 63 cents a mile for. When will Keep on Trucking, Inc. be the better choice for Jamal? Solution. The 2 important quantities in this problem are the cost and the number of miles driven. Because we have 2 companies to consider, we will define 2 functions in Table 1. Input letter 1D451. distance driven in miles, output, letter 1D43, letter 1D451, cost in dollars for renting from Keep On Trucking, letter 1D440, letter 1D451, cost in dollars for renting from Move It Your Way, initial value upfront fee, letter 1D430, 0 equals 20, and letter 1D440, 0 equals 16. Rate of change letter 1D43, letter 1D451 equals $0. 59. Mile and letter 1D443, letter 1D451 equals $0. 63. Mile. Table 1. A linear function is of the form letter 1D453. Letter 1D465 equals letter 1D45A letter 1D465 plus letter 1D44F. Using the rates of change and initial charges, we can write the equations. Letter 1D43, letter 1D451, letter 1D440, letter 1D451 equals 0. 59D plus 200, 63D plus 16. Using these equations, we can determine when Keep On Trucking, Inc. will be the better choice. Because all we have to make that decision from is the costs, we are looking for when Move It Your Way will cost less, or when letter 1D43, letter 1D451, letter 1D440, letter 1D451. The solution pathway will lead us to find the equations for the two functions, find the intersection, and then see where the letter 1D43, letter 1D451 function is smaller. These graphs are sketched in Figure 6, with letter 1D43, letter 1D451. In blue, graph of MD equals 0, 63 plus 16 and KD equals 0, 59M plus 20. The x-axis goes from 0 to 160, and the y-axis goes from 0 to 120, both in intervals of 10. MD has a slope of 0, 63, and a y-intercept of 20, while KD has a slope of 0, 59, and a y-intercept of 16. The two lines intersect at 180. Figure 6. To find the intersection, we set the equations equal and solve. Letter 1D43, letter 1D451, 0. 59 letter 1D451 plus 204,100 letter 1D451 equals letter 1D440, letter 1D451, 0. 63D plus 160. 04 letter 1D451 letter 1D451, 100. This tells us that the cost from the two companies will be the same if 100 miles are driven, either by looking at the graph or noting that letter 1D43, letter 1D451, is growing at a slower rate. We can conclude that Keep On Trucking, Inc. will be the cheaper price when more than 100 miles are driven, that is letter 1D451, 100. Media. Access this online resource for additional instruction and practice with linear function models. Interpreting a linear function. 4-2 section exercises. Verbal. 1. Explain how to find the input variable in a word problem that uses a linear function. 2. Explain how to find the output variable in a word problem that uses a linear function. 3. Explain how to interpret the initial value in a word problem that uses a linear function. 4. Explain how to determine the slope in a word problem that uses a linear function. Algebraic. 5. Find the area of a parallelogram bounded by the y-axis. The line letter 1D465 equals 3. The line letter 1D453, letter 1D465, equals 1 plus 2 letter 1D465, and the line parallel to letter 1D453, letter 1D465, passing through 27. 6. Find the area of a triangle bounded by the x-axis. The line letter 1D453, letter 1D465, equals 12 13 letter 1D465, and the line perpendicular to letter 1D453, letter 1D465, that passes through the origin. 7. Find the area of a triangle bounded by the y-axis. The line letter 1D453, letter 1D465, equals 967 letter 1D465, and the line perpendicular to letter 1D453, letter 1D465, that passes through the origin. 8. Find the area of a parallelogram bounded by the x-axis. The line letter 1D454, letter 1D465, equals 2. The line letter 1D453, letter 1D465, equals 3 letter 1D465, and the line parallel to letter 1D453, letter 1d465. Passing through 61. For the following exercises, consider this scenario. A town's population has been decreasing at a constant rate. In 2010, the population was 5,900. By 2012, the population had dropped to 4,700. Assume this trend continues. 9. Predict the population in 2016. 10. Identify the year in which the population will reach 0. For the following exercises, consider this scenario. A town's population has been increased at a constant rate. In 2010, the population was 46,020. By 2012, the population had increased to 52,070. Assume this trend continues. 11. Predict the population in 2016. 12. Identify the year in which the population will reach 75,000. For the following exercises, consider this scenario. A town has an initial population of 75,000. It grows at a constant rate of 2,500 per year for 5 years. 13. Find the linear function that models the town's population, letter 1d443, as a function of the year, letter 1d461, where letter 1d461 is the number of years since the model began. 14. Find a reasonable domain and range for the function letter 1d443. 15. If the function letter 1d443 is graphed, find and interpret the x and y intercepts. 16. If the function letter 1d443 is graphed, find and interpret the slope of the function. 17. When will the population reach 100,000? 18. What is the population in the year 12 years from the onset of the model? For the following exercises, consider this scenario. The weight of a newborn is 75 pounds. The baby gained 1/2 pound a month for its first year. 19. Find the linear function that models the baby's weight, letter 1d44a, as a function of the age of the baby, in months, letter 1d461. 20. Find a reasonable domain and range for the function letter 1d44a. 21. If the function letter 1d44a is graphed, find and interpret the x and y intercepts. 22. If the function w is graphed, find and interpret the slope of the function. 23. When did the baby weigh 4 pounds? 24. What is the output when the input is 6.2? For the following exercises, consider this scenario. The number of people afflicted with the common cold in the winter months steadily decreased by 205 each year from 2005 until 2010. In 2005, 12,025 people were inflicted. 25. Find the linear function that models the number of people inflicted with the common cold, letter 1d436, as a function of the year, letter 1d461. 26. Find a reasonable domain and range for the function letter 1d436. 27. If the function letter 1d436 is graphed, find and interpret the x and y intercepts. 28. If the function letter 1d436 is graphed, find and interpret the slope of the function. 29. When will the number of people afflicted with the common cold reach 0? 30. In what year will the number of people afflicted with the common cold be 9,700? Graphical. For the following exercises, use the graph in Figure 7, which shows the profit, letter 1d466, in thousands of dollars, of a company in a given year, letter 1d461, where letter 1d461 represents the number of years since 1980. Graph of a decreasing line from 15, 150 to 25, 130. The x-axis goes from 0 to 30 in intervals of 5, and the y-axis goes from 125 to 155 in intervals of 5. Figure 7, 31. Find the linear function letter 1d466, where letter 1d466 depends on letter 1d461. The number of years since 1980, 32. Find and interpret the y-intercept, 33. Find and interpret the x-intercept, 34. Find and interpret the slope. For the following exercises, use the graph in Figure 8, which shows the profit, letter 1d466, in thousands of dollars, of a company in a given year, letter 1d461, where letter 1d461 represents the number of years since 1980. Graph of a line from 15, 150 to 25, 450. The x-axis goes from 0 to 30 in intervals of 5, and the y-axis goes from 0 to 500 in intervals of 50. Figure 8, 35. Find the linear function letter 1d466, where letter 1d466 depends on letter 1d461. The number of years since 1980. 36. Find and interpret the y-intercept. 37. Find and interpret the x-intercept. 38. Find and interpret the slope. Numeric. For the following exercises, use the median home values in Mississippi and Hawaii, adjusted for inflation, shown in Table 2. Assume that the house values are changing linearly. Year Mississippi, Hawaii. 1950-25, $270, $4,400. 2071, $272,700. Table 2. 39. In which state have home values increased at a higher rate? 40. If these trends were to continue, what would be the median home value in Mississippi in 2010? 41. If we assume the linear trend existed before 1950 and continues after 2000, the two states' median house values will be, or were, equal in what year? The answer might be absurd. For the following exercises, use the median home values in Indiana and Alabama, adjusted for inflation, shown in Table 3. Assume that the house values are changing linearly. Year Indiana, Alabama. 1950-30, 7, $727,100. 2094, $380, $5,100. Table 3. 42. In which state have home values increased at a higher rate? 43. If these trends were to continue, what would be the median home value in Indiana in 2010? 44. If we assume the linear trend existed before 1950 and continues after 2000, the two states' median house values will be, or were, equal in what year? The answer might be absurd. Real-world applications. 45. In 2004, a school population was 1,001. By 2008, the population had grown to 1,697. Assume the population is changing linearly. A. How much did the population grow between the year 2004 and 2008? B. How long did it take the population to grow from 1,001 students to 1,697 students? C. What is the average population growth per year? D. What was the population in the year 2000? E. Find an equation for the population, letter 1d443, of the school T years after 2000. F. Using your equation, predict the population of the school in 2011. 46. In 2003, a town's population was 1,431. By 2007, the population had grown to 2,134. Assume the population is changing linearly. A. How much did the population grow between the year 2003 and 2007? B. How long did it take the population to grow from 1,431 people to 2,134 people? C. What is the average population growth per year? D. What was the population in the year 2000? E. Find an equation for the population, letter 1d443, of the town, letter 1d461, years after 2000. F. Using your equation, predict the population of the town in 2014. 47. A phone company has a monthly cellular plan where a customer pays a flat monthly fee and then a certain amount of money per minute used for voice or video calling. If a customer uses 410 minutes, the monthly cost will be $71, $50. If the customer uses 720 minutes, the monthly cost will be $118. A. Find a linear equation for the monthly cost of the cell plan as a function of x, the number of monthly minutes used. B. Interpret the slope and y-intercept of the equation. C. Use your equation to find the total monthly cost if 687 minutes are used. 48. A phone company has a monthly cellular data plan where a customer pays a flat monthly fee of $10 and then a certain amount of money per megabyte, MB, of data used on the phone. If a customer uses 20 MB, the monthly cost will be $11, $20. If the customer uses 130 MB, the monthly cost will be $17, $80. A. Find a linear equation for the monthly cost of the data plan as a function of letter 1d465, the number of MB used. B. Interpret the slope and y-intercept of the equation. C. Use your equation to find the total monthly cost if 250 MB are used. 49. In 1991, the moose population in a park was measured to be 4,360. By 1999, the population was measured again to be 5,880. Assume the population continues to change linearly. A. Find a formula for the moose population, P since 1991. B. What does your model predict the moose population to be in 2003? 50. In 2003, the owl population in a park was measured to be 340. By 2007, the population was measured again to be 285. The population changes linearly. Let the input be years since 2003. A. Find a formula for the owl population, letter 1D443. Let the input be years since 2003. B. What does your model predict the owl population to be in 2012? 51. The Federal Helium Reserve held about 16 billion cubic feet of helium in 2010 and is being depleted by about 1 billion cubic feet each year. Give a linear equation for the remaining federal helium reserves, letter 1D445. In terms of letter 1D461, the number of years since 2010. B. In 2015, what will the helium reserves be? C. If the rate of depletion doesn't change, in what year will the federal helium reserve be depleted? 52. Suppose the world's oil reserves in 2014 are 1,820 billion barrels. If, on average, the total reserves are decreasing by 25 billion barrels of oil each year, give a linear equation for the remaining oil reserves, letter 1D445. In terms of letter 1D461, the number of years since now. B. 7 years from now, what will the oil reserves be? C. If the rate at which the reserves are decreasing is constant, when will the world's oil reserves be depleted? 53. You are choosing between two different prepaid cell phone plans. The first plan charges a rate of 26 cents per minute. The second plan charges a monthly fee of $19, $95 plus 11 cents per minute. How many minutes would you have to use in a month in order for the second plan to be preferable? 54. You are choosing between two different window washing companies. The first charges $5 per window. The second charges a base fee of $40 plus $3 per window. How many windows would you need to have for the second company to be preferable? 55. When hired at a new job selling jewelry, you are given two pay options. Option A. Base salary of $17,000 a year with a commission of 12% of your sales. Option B. Base salary of $20,000 a year with a commission of 5% of your sales. How much jewelry would you need to sell for option A to produce a larger income? 56. When hired at a new job selling electronics, you are given two pay options. Option A. Base salary of $14,000 a year with a commission of 10% of your sales. Option B. Base salary of $19,000 a year with a commission of 4% of your sales. How much electronics would you need to sell for option A to produce a larger income? 57. When hired at a new job selling electronics, you are given two pay options. Option A. Base salary of $20,000 a year with a commission of 12% of your sales. Option B. Base salary of $26,000 a year with a commission of 3% of your sales. How much electronics would you need to sell for option A to produce a larger income? 58. When hired at a new job selling electronics, you are given two pay options. Option A. Base salary of $10,000 a year with a commission of 9% of your sales. Option B. Base salary of $20,000 a year with a commission of 4% of your sales. How much electronics would you need to sell for option A to produce a larger income? Learning objectives. In this section, you will draw and interpret scatter diagrams. Use a graphing utility to find the line of best fit. Distinguish between linear and nonlinear relations. Fit a regression line to a set of data, and use the linear model to make predictions. A professor is attempting to identify trends among final exam scores. His class has a mixture of students, so he wonders if there is any relationship between age and final exam scores. One way for him to analyze the scores is by creating a diagram that relates the age of each student to the exam score received. In this section, we will examine one such diagram known as a scatter plot. Drawing and interpreting scatter plots. A scatter plot is a graph of plotted points that may show a relationship between two sets of data. If the relationship is from a linear model or a model that is nearly linear, the professor can draw conclusions using his knowledge of linear functions. Figure 1 shows a sample scatter plot. Scatter plot, titled Final Exam Score vs. Age. The x-axis is the age, and the y-axis is the final exam score. The range of ages are between 20s, 50s, and the range for scores are between upper 50s and 90s. Figure 1, a scatter plot of age and final exam score variables. Notice this scatter plot does not indicate a linear relationship. The points do not appear to follow a trend. In other words, there does not appear to be a relationship between the age of the student and the score on the final exam. Example 1. Using a scatter plot to investigate cricket chirps, the table below shows the number of cricket chirps in 15 seconds for several different air temperatures in degrees Fahrenheit 5. Plot this data and determine whether the data appears to be linearly related. Chirps 44, 35, 20, 4, 33, 31, 35, 18, 5, 37, 26, temperature 80, 570, 557, 66, 68, 72, 52, 73, 553. Table 1 cricket chirps versus air temperature. Solution. Plotting this data, as depicted in Figure 2, suggests that there may be a trend. We can see from the trend in the data that the number of chirps increases as the temperature increases. The trend appears to be roughly linear, though certainly not perfectly so. Scatter plot, titled Cricket Chirps versus Air Temperature. The x-axis is the cricket chirps in 15 seconds, and the y-axis is the temperature, F. The line regression is generally positive. Figure 2. Finding the line of best fit. Once we recognize a need for a linear function to model that data, the natural follow-up question is, what is that linear function? One way to approximate our linear function is to sketch the line that seems to best fit the data. Then we can extend the line until we can verify the y-intercept. We can approximate the slope of the line by extending it until we can estimate the rice run. Example 2. Finding a line of best fit. Find a linear function that fits the data in Table 1 by eyeballing a line that seems to fit. Analysis. This linear equation can then be used to approximate answers to various questions we might ask about the trend. Recognizing interpolation or extrapolation. While the data for most examples does not fall perfectly on the line, the equation is our best guess as to how the relationship will behave outside of the values for which we have data. We use a process known as interpolation when we predict a value inside the domain and range of the data. The process of extrapolation is used when we predict a value outside the domain and range of the data. Figure 4 compares the two processes for the cricket chirp data addressed in Example 2. We can see that interpolation would occur if we used our model to predict temperature when the values for chirps are between 18.5 and 44. Extrapolation would occur if we used our model to predict temperature when the values for chirps are less than 18.5 or greater than 44. There is a difference between making predictions inside the domain and range of values for which we have data and outside that domain and range. Predicting a value outside of the domain and range has its limitations. When our model no longer applies after a certain point, it is sometimes called model breakdown. For example, predicting a cost function for a period of 2 years may involve examining the data where the input is the time in years and the output is the cost. But if we try to extrapolate a cost when letter 1D465 equals 50, that is in 50 years, the model would not apply because we could not account for factors 50 years in the future. Scatter plot showing the line of best fit. It is titled Cricket Chirps vs. Air Temperature. The x-axis is C, number of chirps, and the y-axis is Tc, temperature F. The area around the scattered points is enclosed in a box labeled interpolation. The area outside of this box is labeled extrapolation. Figure 4 interpolation occurs within the domain and range of the provided data, whereas extrapolation occurs outside. Interpolation and extrapolation. Different methods of making predictions are used to analyze data. The method of interpolation involves predicting a value inside the domain and/or range of the data. The method of extrapolation involves predicting a value outside the domain and/or range of the data. Model breakdown occurs at the point when the model no longer applies. Example 3. Understanding interpolation and extrapolation. Use the cricket data from Table 1 to answer the following questions. A. Would predicting the temperature when crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? Make the prediction and discuss whether it is reasonable. B. Would predicting the number of chirps crickets will make at 40 degrees be interpolation or extrapolation? Make the prediction and discuss whether it is reasonable. Solution. The number of chirps in the data provided varied from 18.5 to 44. A prediction at 30 chirps per 15 seconds is inside the domain of our data, so would be interpolation. Using our model, T 30 equals 30 plus 1. 230, 66 degrees. Based on the data we have, this value seems reasonable. B. The temperature values varied from 52 to 80. 5. Predicting the number of chirps at 40 degrees is extrapolation because 40 is outside the range of our data. Using our model, 40 equals 30 plus 1. 2 letter 1d450, 10 equals 1. 2 C letter 1d450, approximately 8. 33. We can compare the regions of interpolation and extrapolation using Figure 5. Scatter plot showing the line of best fit and where interpolation and extrapolation occurs. It is titled Cricket Chirps versus Air Temperature. The x-axis is C, number of chirps, and the y-axis is T, C, temperature, F. An additional point is plotted inside of the box to represent an interpolated point. There is another additional point plotted outside of the box to represent an extrapolated point. Figure 5. Analysis. Our model predicts the crickets would chirp 33 times in 15 seconds. While this might be possible, we have no reason to believe our model is valid outside the domain and range. In fact, generally crickets stop chirping altogether below around 50 degrees. Try it 1. According to the data from Table 1, what temperature can we predict it is if we counted 20 chirps in 15 seconds? Finding the line of best fit using a graphing utility. While eyeballing a line works reasonably well, there are statistical techniques for fitting a line to data that minimize the differences between the line and data value 6. One such technique is called least squares regression and can be computed by many graphing calculators, spreadsheet software, statistical software, and many web-based calculators 7. Least squares regression is one means to determine the line that best fits the data, and here we will refer to this method as linear regression. How to. Given data of input and corresponding outputs from a linear function, find the best fit line using linear regression. Enter the input in list 1, L1. Enter the output in list 2, L2. On a graphing utility, select linear regression linreg. Example 4. Finding a least squares regression line. Find the least squares regression line using the cricket chirp data in Table 2. Solution. Enter the input chirps in list 1, L1. Enter the output temperature in list 2, L2. See Table 2. L1 44 35 20, 4 33 31 35 18, 5 37 26, L2 80, 570, 557 66 68 72 52 73, 553. Table 2. On a graphing utility, select linear regression, linreg. Using the cricket chirp data from earlier, with technology we obtain the equation. Letter 1d447, letter 1d450 equals 30. 281 plus 1. 143c. Analysis. Notice that this line is quite similar to the equation we eyeballed, but should fit the data better. Notice also that using this equation would change our prediction for the temperature when hearing 30 chirps in 15 seconds from 66 degrees to letter 1d447, 30 equals 30. 281 plus 1, 143, 30 equals 64. 571 approximately 64. 6 degrees. The graph of the scatter plot with the least squares regression line is shown in Figure 6. Scatter plot showing the line of best fit, T, C, equals 30 281 plus 1, 143c. It is titled Cricket Chirps versus Air Temperature. The x-axis is C, number of chirps, and the y-axis is T, C, temperature, F. Figure 6. Q&A. Will there ever be a case where two different lines will serve as the best fit for the data? No, there is only one best fit line, distinguishing between linear and nonlinear models. As we saw above with the cricket chirp model, some data exhibit strong linear trends, but other data, like the final exam scores plotted by age, are clearly nonlinear. Most calculators and computer software can also provide us with the correlation coefficient, which is a measure of how closely the line fits the data. Many graphing calculators require the user to turn a diagnostic on selection to find the correlation coefficient, which mathematicians label as R. The correlation coefficient provides an easy way to get an idea of how close to a line the data falls. We should compute the correlation coefficient only for data that follows a linear pattern or to determine the degree to which a data set is linear. If the data exhibits a nonlinear pattern, the correlation coefficient for a linear regression is meaningless. To get a sense for the relationship between the value of R and the graph of the data, Figure 7 shows some large data sets with their correlation coefficients. Remember, for all plots, the horizontal axis shows the input and the vertical axis shows the output. Correlation coefficients values range from -1, 0, 1, 0. Collections of dots representing an example of each kind of correlation coefficient are plotted underneath them, the closer to 1. The more the points are grouped tightly to form a line in the positive direction, the closer to -1. The more the points are grouped tightly to form a line in the negative direction. The closer to 0, the points are very scattered and do not form a line. Several shapes are displayed at the bottom row, none of which are lines, but all of them have values of 0. Figure 7 plotted data and related correlation coefficients. Credit: Denys Boigelat, Wikimedia Commons. Correlation coefficient. The correlation coefficient is a value, R, between 1 and 1. Letter 1d45f0 suggests a positive, increasing relationship. Letter 1d45f0 suggests a negative, decreasing relationship. The closer the value is to 0, the more scattered the data. The closer the value is to 1 or 1, the less scattered the data is. Example 5. Finding a correlation coefficient. Calculate the correlation coefficient for cricket chirp data in Table 1. Solution. Because the data appear to follow a linear pattern, we can use technology to calculate R. Enter the inputs and corresponding outputs and select the linear regression. The calculator will also provide you with the correlation coefficient, letter 1d45f equals 0, 9509. This value is very close to 1, which suggests a strong increasing linear relationship. Note: for some calculators, the diagnostics must be turned on in order to get the correlation coefficient when linear regression is performed. Second 0 alpha x 1, then scroll to diagnosticson, fitting a regression line to a set of data. Once we determine that a set of data is linear using the correlation coefficient, we can use the regression line to make predictions. As we learned above, a regression line is a line that is closest to the data in the scatter plot, which means that only one such line is a best fit for the data. Example 6. Using a regression line to make predictions. Gasoline consumption in the United States has been steadily increasing. Consumption data from 1994 to 2004 is shown in Table 3.8. Determine whether the trend is linear, and if so, find a model for the data. Use the model to predict the consumption in 2008. Year 94, 95, 96, 97, 98, 99, 0, 10, 20, 304. Consumption, billions of gallons. 113, 116, 118, 119, 120, 3, 125, 126, 128, 130, 133, 136. Table 3. The scatter plot of the data, including the least squares regression line, is shown in Figure 8. Scatter plot showing the line of best fit. It is titled Gas Consumption vs. Year. The x-axis is year after 1994, and the y-axis is gas consumption, billions of gallons. The points are strongly positively correlated, and the line of best fit goes through most of the points completely. Figure 8. Solution. We can introduce a new input variable, t, representing years since 1994. The least squares regression equation is letter 1d436, letter 1d461 equals 113, 318 plus 2, 209t. Using technology, the correlation coefficient was calculated to be 0, 9965, suggesting a very strong increasing linear trend. Using this to predict consumption in 2008, letter 1D461 equals 14. Letter 1D436, 14 equals 113. 318 plus 2. 209, 14, equals 144. 244. The model predicts 244 billion gallons of gasoline consumption in 2008. Try it too. Use the model we created using technology in example 6 to predict the gas consumption in 2011. Is this an interpolation or an extrapolation? Media. Access these online resources for additional instruction and practice with fitting linear models to data. Introduction to Regression Analysis. Linear regression. 4. 3-section exercises. Verbal. 1. Describe what it means if there is a model breakdown when using a linear model. 2. What is interpolation when using a linear model? 3. What is extrapolation when using a linear model? 4. Explain the difference between a positive and a negative correlation coefficient. 5. Explain how to interpret the absolute value of a correlation coefficient. Algebraic. 6. A regression was run to determine whether there is a relationship between hours of TV watched per day, X, and number of sit-ups a person can do, Y. The results of the regression are given below. Use this to predict the number of sit-ups a person who watches 11 hours of TV can do. Letter 1D466 equals letter 1D44E letter 1D465 plus letter 1D44F letter 1D44E equals minus 1. 340, 1 letter 1D44F equals 32. 234 letter 1D45F equals minus 0. 896. 7. A regression was run to determine whether there is a relationship between the diameter of a tree, letter 1D465, in inches and the tree's age, letter 1D466. In years, the results of the regression are given below. Use this to predict the age of a tree with diameter 10 inches. Letter 1D466 equals letter 1D44E letter 1D465 plus letter 1D44F letter 1D44E equals 6. 301 letter 1D44F equals minus 1. 044 letter 1D45F equals 0. 970. For the following exercises, draw a scatter plot for the data provided. Does the data appear to be linearly related? 80246 22 19 15 11 6 2 9 1 2 3 4 5 6 46 50 59 75 100 100 36 10 100 250 300 450 600 750 12 12 6 13 1 14 14 5 15 2 11 1 3 5 7 9 11 1 9 28 65 100 25 216 12. For the following data, draw a scatter plot. If we wanted to know when the population would reach 15,000, would the answer involve interpolation or extrapolation? Eyeball the line and estimate the answer. Year population: 1990 11, 500. 1995 12, 100. 2012 700. 2005 13, 000. 2010 13, 750. 13. For the following data, draw a scatter plot. If we wanted to know when the temperature would reach 28 degrees F, would the answer involve interpolation or extrapolation? Eyeball the line and estimate the answer. Temperature: degrees F 16 18 20 25 30. Time: seconds 46 50 54 55 62. Graphic. For the following exercises, match each scatterplot with one of the 4 specified correlations in Figure 9 and Figure 10. Side-by-side scatter plots. The first is a scattered correlation in the positive direction. The second is a scattered correlation in the negative direction. Figure 9. Side-by-side scatter plots. The first has a strong negative correlation with all the points spaced out evenly near the top and center, but more spread out near the bottom. The second has a strong positive correlation, with the points more spread out near the bottom and closer together near the center and top. Figure 10. 14, letter 1D45F equals 0, 95. 15, letter 1D45F equals minus 0, 89. 16, letter 1D45F equals minus 0, 26. 17, letter 1D45F equals minus 0, 39. For the following exercises, draw a best fit line for the plotted data. 18. Scatter plot with a domain of 0 to 10 and a range of 4 to 9. The points are at 5, 214, 2, 356, 456, 5, 556, 8, 77, 4, 88, 5, 98, and 109, 19. Scatter plot with a domain of 0 to 10 and a range of -1 to 4. The points are at 1, 5, 15, -01, 211, 9, 3415, 452, 5, 5, 82, 2, 683, 8, 783, 6, 8, 82, and 102, 4, 20. Scatter plot with a domain of 0 to 10 and range of 0 to 7 with the points 7, 3, 17, 226, 3, 67, 486, 2, 5, 84, 663, 8, 792, 4, 8, 82, and 101, 21. Scatter plot with a domain of 0 to 10 and a range of 2 to 6 with the points 2, 1, 13, 9, 2, 13, 6, 363, 9, 4, 44, 564, 2, 685, 785, 95, 6, and 106, numeric. 22. The U.S. Census tracks the percentage of persons 25 years or older who are college graduates. That data for several years is given in Table 4. 9. Determine whether the trend appears linear. If so, and assuming the trend continues, in what year will the percentage exceed 35%? Year percent graduates, 1990 21, 3, 1992 21, 4, 1994 22, 2, 1996 23, 6, 1998 24, 4, 2025, 6, 2002 26, 7, 2004 27, 7, 2006 28, 2008 29, 4. Table 4. 23. The U.S. import of wine in hectoliters for several years is given in Table 5. Determine whether the trend appears linear. If so, and assuming the trend continues, in what year will imports exceed 12,000 hectoliters? Year imports: 1992, 2,665, 1994, 2,688, 1996, 3,565, 1998, 4,129, 2004, 1,584, 2002, 5,655, 2004, 6,549, 2006, 7,950, 2008, 8,487, 2009, 9,462. Table 5. 24. Table 6 shows the year and the number of people unemployed in a particular city for several years. Determine whether the trend appears linear. If so, and assuming the trend continues, in what year will the number of unemployed reach 5? Year number unemployed: 1990, 750, 1992, 670, 1994, 650, 1996, 605, 1998, 550, 2,510, 2002, 460, 2004, 420, 2006, 380, 2008, 320. Table 6. Technology. For the following exercises, use each set of data to calculate the regression line using a calculator or other technology tool, and determine the correlation coefficient to 3 decimal places of accuracy. 25, x, 8, 15, 26, 31, 56, y, 23, 41, 53, 72, 103. 26, x, 5, 7, 10, 12, 15, y, 4, 12, 17, 22, 24. 27, x, y, x, y, 3, 21, 9, 10, 18, 54, 4, 22, 22, 11, 15, 76, 5, 22, 74, 12, 13, 68, 6, 22, 26, 13, 14, 1, 7, 20, 78, 14, 14, 2, 8, 17, 6, 15, 11, 94, 9, 16, 52, 16, 12, 76, 28, x, y, 444, 8, 543, 1, 638, 8, 739, 8:38, 9:32, 7, 10:30, 1, 11:29, 3, 12:27, 13:25, 8, 29, x, 21, 25, 30, 30, 1, 40, 50, y, 17, 11, 2, 1, 18, 40, 30, x, y, 102,000, 80, 1,798, 61,589, 55, 1,580, 40, 1,390, 21,202, 31, x, 900, 988, 1,000, 1,010, 1,200, 1,205, y, 70, 80, 82, 84, 105, 108. Extensions. 32. Graph letter 1D453, letter 1D465 equals 0, 5x plus 10. Pick a set of 5 ordered pairs using inputs, and use linear regression to verify that the function is a good fit for the data. 33. Graph letter 1D453, letter 1D465 equals minus 2 letter 1D465 minus 10. Pick a set of 5 ordered pairs using inputs, and use linear regression to verify the function. For the following exercises, consider this scenario. The profit of a company decreased steadily over a 10-year span. The following ordered pairs shows dollars and the number of units sold in hundreds and the profit in thousands of dollars over the 10-year span. Number of units sold, profit for specific recorded years. 46, 1, 600, 48, 1, 550, 50, 1, 505, 52, 1, 540, 54, 1, 495. 34. Use linear regression to determine a function, letter 1D443, where the profit in thousands of dollars depends on the number of units sold in hundreds. 35. Find to the nearest tenth and interpret the x-intercept. 36. Find to the nearest tenth and interpret the y-intercept. Real-world applications. For the following exercises, consider this scenario. The population of a city increased steadily over a 10-year span. The following ordered pairs shows the population and the year over the 10-year span. Population, year, for specific recorded years. 2,500, 2,000, 2,650, 2001, 3,000, 2003, 3,500, 2006, 4,200, 2010. 37. Use linear regression to determine a function, letter 1D466, where the year depends on the population. Round to 3 decimal places of accuracy. 38. Predict when the population will hit 8,000. For the following exercises, consider this scenario. The profit of a company increased steadily over a 10-year span. The following ordered pairs show the number of units sold in hundreds and the profit in thousands of dollars over the 10-year span. Number of units sold, profit for specific recorded years. 46, 250, 48, 305, 50, 350, 52, 390, 54, 410. 39. Use linear regression to determine a function y, where the profit in thousands of dollars depends on the number of units sold in hundreds. 40. Predict when the profit will exceed $1 million. For the following exercises, consider this scenario. The profit of a company decreased steadily over a 10-year span. The following ordered pairs show dollars and the number of units sold in hundreds and the profit in thousands of dollars over the 10-year span. Number of units sold, profit for specific recorded years. 46, 250, 48, 225, 50, 205, 52, 180, 54, 165. 41. Use linear regression to determine a function y, where the profit in thousands of dollars depends on the number of units sold in hundreds. 42. Predict when the profit will dip below the $25,000 threshold.